Well, hello and welcome everybody to the second virtual wind conference brought to you by Offshore Renewable Energy Catapult and Fraunhofer IWES. We're going to look at some of the current challenges faced by offshore wind in the North Sea. This follows our successful first online conference held back in April and is underpinned by the very strong collaboration we have in place between ORE Catapult and Fraunhofer IWES, particularly in the areas of research infrastructures, materials, structures, and turbine technology demonstration. Andreas and I and the team have known each other for quite some time, and I'm very pleased that our relationship is getting stronger by the day. And as we all know, there are lots of technical challenges that we need to be solving through the field of innovation and applied research. So that's terrific. Our collaboration is cemented through our common membership of the European Energy Research Alliance Joint Programme for Wind. In short, that's called ERA JP Wind. As I am sure you all know, offshore wind has some major research and innovation challenges ahead to meet the 2030 and 2050 targets. This requires widespread collaboration across the research community, and this widespread collaboration is served well by the ERA JP Wind platform. We also wanted to highlight the importance of data sharing, which is widely regarded by stakeholders across the sector as being critical to technology advancement and enabling improvements in the reliability and optimization of wind turbine assets in operation. ORE Catapult and Fraunhofer IWES are in the unique position of operating demonstration turbines and coordinating large data sharing initiatives, e.g. Sparta and Alpha Ventus. And we will continue to share experiences and promote learnings from these activities, as well as continuing our wider collaboration stroke data sharing with third parties across the sector. Finally, the last point we wanted to make today concerns the importance of integrating offshore wind into the energy systems of the future. The need for this has never been so clear. This will require a wider systems perspective and also require the development of energy storage solutions and multi-energy vector solutions, including the potential use of hydrogen. With this in mind, the demonstration of these solutions on a grand scale is at a key stage in the process, and it is encouraging to see ORE Catapult and Fraunhofer IWES back developments in the UK, such as Leavenmouth at Milford Haven, and in Germany at Bremerhaven, for the demonstration of these technologies. So I'm very excited about what we're going to be talking about today. I'm very excited about the collaboration that we have with Fraunhofer, and I'm very excited about looking forward to engaging with you all. And I thank you all for joining us today. I just wanted to make those brief words to welcome you and to talk about the prospects that we have in doing more on research and innovation together. And with that, I will hand over to my good colleague, Andreas. Andreas, over to you.
Thank you very much, Andrew. Thank you for starting the session today. And also a warm welcome from my side to all participants. And yeah, I would like to give a little bit background on the format of this event. So it's basically born out of the Corona environment, which we have been facing suddenly in March. And although all the colleagues of us have been working hard to overcome the challenges of this time, and I think we did great in doing so, we found out that we are missing a couple of things. And one is the topic of exchanging ideas. Traveling to meet colleagues from other organizations was an important element of our research work, and we're just missing that. And so the idea is that with this format, the Virtual Wind Conference, we try to overcome this deficiency. Of course, it's still better to meet people face to face, but I think better to have things like that than nothing. And so when we tried the waters first in April, as Andrew mentioned, on the topic of turbine-related offshore challenges, the participation was great and the feedback encouraging. And so here we are again, today with a focus on topics related to the planning and O&M phase of wind projects. And so I hope that all participants will also find this as positive as the last event we did. And so I just want to give you a couple of ideas what we're planning with you today and who's taking you through the day. So we have a morning session, and we're looking there at site surveys and foundation designs and monitoring topics, containing 3 interesting presentation themes provided by both the industry and research colleagues, and shared by my colleague Bernhard Lange. He's a division director at Fraunhofer IWES, and he's a long-time veteran of the industry. The afternoon session moves on to the topic of O&M concept optimization, chaired by Paula, head of electrical research from Catapult, and also veteran of the industry. And again, the session provides 3 more excellent themes, providing both industry and research perspective. I have also a housekeeping issue I want to mention before we start with all these sessions. This is that we ask you and we make you stay muted through the presentation. But at the end of each presentation, you will have the opportunity to ask questions to the speaker using the Q&A function of this format. So please feel free to participate, and we really encourage you to ask questions, because I mean this is one of the main purposes of this event. You also should note that the session will be recorded, so by participating you agree to this recording. But before we start the session today, and I do not want to overburden you with all these formalities, but it's about content, and therefore to warm you up for today's sessions, we have a keynote lecture by Ørsted, one of the leading offshore turbine operators globally. And for the detailed introduction of the first speaker, I will hand over now to Bernhard. And I wish you an interesting day with lots of opportunities for exchanging ideas and generally staying in touch. And so thank you, everybody, for participating. Thank you to the speakers already for taking the effort of preparing something for today. Yeah, I'm looking forward to an interesting day, interesting topics, and a good discussion. Thank you. And now, Bernhard, you take over.
Yeah, thank you, Andreas, for this introduction, and welcome also from my side to all of you to this second virtual wind conference we are having today. As Andreas already mentioned, there's a possibility to ask questions. Please use the question and answer button of the conference to do that. You can write questions already during the talk or after the talk. And then after the talk, I will pose the questions to the speaker, and we will have a little discussion in this way. And now let's start. It's my special pleasure to introduce to you Paula Segelken, our keynote speaker for today. Paula works at Ørsted as a senior project lead, where she's responsible for setting up the operational strategy of development projects in existing as well as new offshore markets. And before joining Ørsted, she has been involved in the regulatory work at the German Association for Offshore Wind Farm Operators, and also worked for the turbine manufacturers Siemens Gamesa, as well as Goldwind in China. Paula, it's great to have you here. The screen is yours. Usually I say the floor is yours, but today I think it's better to say the screen is yours. We are looking forward to your presentation.
Yeah, thank you very much. I will share my screen. 1 second. Thank you very much for this opportunity to speak here, Andreas and Andrew, and for the kind introduction, Bernhard. It's really a pleasure to be here. Yeah, as you've mentioned, Andreas, it's going towards more virtual conferences now. This is my first virtual conference, so I'm very excited to be here actually. And it's I hope that some of this stays for whenever we go out of the corona situation, because this is actually one of the parts how we can contribute to a bit less of global warming and less of global traffic. So I really hope we can continue doing that. as Bernhard has said, I'm working as operations senior project lead in operations development projects. So I'm setting up operations in our new projects. And I would like to focus today on one of the factors that I see in operations, how operations develops actually, which is a trend towards more data-driven operations. And I was kindly provided by input from two colleagues there that I would like to walk you through. But before we go there, I was told that we have a broad audience here from all over the world, all developers, suppliers, researchers. So just to give you a brief introduction on what Ørsted is, maybe I would start with that one, in case you haven't heard of us. So I would like to start with our vision. Let's create a world that runs entirely on green energy. This is what Ørsted stands for. And this is actually what we have started looking at very early on, which brought us into the great position that we are in now. This is to just give you a glance at what are we working in. Yes, we are working, we have offshore wind, and about 75% of our capital actually goes into offshore wind, but we're also working a bit on onshore wind and markets and bioenergy. And we have a total of 6.5 employees, 6,500 employees, more or less. So what today we're focusing on is the offshore wind part. And to give you a glance of what we have as experience there, here you can see the map of our wind farms that we have in Europe, US, and Taiwan under operation, but also under construction and under development. And we have actually more than 25 years of experience and track record in the offshore wind business, 26 offshore wind farms in operations. So we have quite a base, 7 gigawatts constructed capacity already. And as I will show you also in the coming slides, looking towards adding some more of gigawatts to that one. But this is just to give you a bit of a background of what we're talking at. It's not only Europe, we have the whole world in the portfolio, and we face the most different challenges in operations there. And that is how you can see, and also within the project phase, I would say, of an offshore wind farm, you need to develop, build, operate and own the wind farm. And this is representing the share of employees working in the different departments. So yes, there is a huge focus on building, constructing the wind farms. This is just very work intense. A lot of engineering and energy goes into that one. But we have more and more wind farms under operations, and you can see that almost a third of our employees working in operations. So we're not only building the wind farm and then letting other people operate it, but we ourselves want to operate the wind farms and want to build the in-house knowledge and capacity to actually do it as good as possible. And that was what I was talking about. Currently, we have about 10 gigawatts of installed capacity, the major share of that being offshore wind. But by 2030, we're looking into 30 gigawatts of installed capacity. And offshore wind will still play a huge part in that one. So we're still being ambitious and we want more. And I was really glad to hear you, Andrew, mention the global warming and the targets for 2030, 2040 that we have, because here you can see it's the UN targets for carbon emission. And we are being really ambitious at Ørsted, and we say that already by 2025, we want to be carbon neutral for our power and heat generation. So we are taking this serious. This is not purely to have a business in offshore wind. We have the vision, we want to create a world, or we have the aim to create a world that runs entirely on green energy, and we want to play our part in that one. But what the focus of today is, or how do we reach that? Because we can't just continue building. We need to get more cost effective, and a big share in that is going bigger in turbines and wind farms. And you have spent the last virtual conference on the topic of turbine development. So this is just to mention, yes, this is a point, and we need to even improve more there. And there are challenges there, but there are also other factors that are contributing to the cost reduction. For example, optimizing manufacturing processes, so just being more efficient and effective in the production of the different technical packages, being more efficient also in the construction period, being able to install with the new technologies, install faster. But then, and this is the big point that I would like to talk about today, or introduce you to the topic today, and then we have some great speakers later going in the details of the different options. There is, we need to reduce the operations and maintenance cost. And one of the ways, and that's the aspect that I would like to talk about today, is that we, instead of purely focusing on the technical package and having the mechanical engineer improving the structural or the geotechnical improving, looking at the soil conditions, is that throughout all these disciplines, we are applying data analysis to support those packages to actually improve even more. And at Ørsted, we have the Ørsted Lab, how we call it. It was established in 2016, and here I have to thank my colleague Simon Forsbørresen for providing me with the slides and allowing me to introduce the lab. Where is he? He is the product manager, and he's actually the head of advanced analytics. The lab was established, as I said, in 2016, and already after a month, they were able to release the first product that already created a great cost saving. So not the technical improvement itself, but only by learning from our data that we have available, and reading and understanding this data, analyzing this data, making improvements that saved us a lot of cost. So how does that work? And I would just like to quickly take you through it, and also try to somehow make a bridge to the other colleagues here and the audience being online. How do you play a role in this one? The input for our Ørsted Lab for advanced analytics is data. So we have all kind of data that is internal. You could see in the overview of the turbine development, we have 1,500 turbines installed. So we have a huge data background where we just have data that we can analyze, but it is not only internal data, we also receive external data. Our suppliers are a key stakeholder in that, in contributing to that, and we need to jointly optimize how we can have the right data. And examples for that would be, for example, measurements from the turbines or the vessels, or even observations from the technicians and weather data. So this is the data that goes in. And then we have the advanced analytics platforms, and this is different domains, applications, tools. So we use data-driven integrity management, for example, to just name some, fleet diagnostics. We have the control and monitoring center. And we use all kinds of different techniques. And just to throw in some buzzwords here, you've all heard of digital twins. So that's actually, we want to have a digital twin of each turbine, of each wind farm that we can analyze. We use simulations. We have predictive and prescriptive models. And what comes out of this advanced analytics, the Ørsted Lab then, is actually, at first we have reports and transparency, so we know the state that our equipment is in, but also optimal maintenance plans and activities, so we can actually improve our inspection plans. And this would be the second quick topic that I would like to talk you through. Also, it comes in 2 slides. And the benefits is how we can see is we have risk reduction and safety improvements, and this is very important, especially for Ørsted. I know everybody in the whole industry has a huge focus on HSE, but especially we're at Ørsted, we want to be focused on HSE. We have a lot of focus on safety, and this is one of the great outcomes that we can have of this one. Then we can obviously extend the lifetime. If we know the state that our turbine is in, we know the age, not the predicted age, but the actual age of our equipment, and we can know for how much longer it will be able to perform. We see production increase, availability increase, and obviously a cost reduction through that one. And just to give you through two examples, because this is very focusing on hypothetically speaking, how does it work, but to give you two examples of what that actually means. So for example, what we can do is we can predict failures and advise to replace before the actual failure. So a cabinet fan in the wind turbine, when the cabinet fan fails, the turbine will stop. So we would like to avoid it stopping. So we can either just go there. If we don't know the state that it is in, we would just need to inspect it very often and replace it very often. But the data-driven model actually that we developed here was able to predict when the fan is about to fail. So before the failure, we can already advise to replace it. And you can see here just an exemplary comparison of cost that we had before. We would have to, when the fan fails, we would realize it onshore. We need to send out technicians. We need to wait for a weather window when we can actually access the turbine and replace. And all of this will be lost revenue because the turbine is stopping at that time. Whereas if we know when the fan will fail, we can search for a perfect weather window to access the turbine. We can make the technicians go out there and just stop the turbine for the specific time that the replacement would need. And by that, we have saved all this cost. So this is one of the examples. Another one would be that we can detect and classify underperformance and give advice to improve there. So we had a software update that resulted in the turbines being curtailed in certain situations. If we didn't have this data analysis, we probably wouldn't have noticed why this underperformance is there. We just see a lost revenue and an underperformance, but we don't know why and how this is happening. But a data-driven model actually detected this underperformance and found out the specific errors in there and the underperformance. And then we could have a focused dialogue with the add-on provider. And this is, again, to put focus on what do the suppliers play as a role in here. We need our tools to be able to be analyzed by data analytics, and then we need an open dialogue with our suppliers to actually take the learnings here and make that improvement. And it was possible here, so the lost revenue could be recovered. And that's just two of the success stories that we had from the Ørsted lab. So far to the Ørsted lab, which is a great thing, and it's actually, we have a lot of visitors there also. It's not only, they don't only do fancy work, it is a fancy office and a fancy environment, which is really nice to work at and to speak to the people there. And as I have mentioned, one of the outcomes is to improve inspection plans. And that would be the second example that I would like to talk you through today. So risk-based inspections is one of the outcomes that we have from the advanced analytics. If we know more about the failure, we can also go more towards risk-based inspections. And the first, I think I don't have to take you through the definition of risk. That's probably all of you know that. But what we actually do is we look at our different components and we analyze them for their different parts that they have. And this is just an example So this would be one component where we look at the different parts and identify with the part how likely is it that this part will fail. This is this part, and then how big would the consequence be if this item fails. So in the example of the fan, the consequence would be really high, because if the fan fails, the production stops. So instead of just inspecting the whole component all the time and looking at everything, we do first an exercise of saying what parts of this components are very critical. And you can see here the dark yellowish red components that we then want to put a special focus on. And focus on them to actually say, okay, when these components fail and use advanced analytics to focus on them and try to be as good as possible in predicting those failures. And what enables us to do it is we have in-house competency. We do project development ourselves. We have, as I mentioned, the 1,500 turbines installed. We do foundation design in-house, O&M and inspection. We do a big share in-house, and we have the asset integrity management. But a big share is the supplier consultation, and I can't get tired of mentioning that. We need to involve everybody, and it's not only suppliers, it's research institutes, it's the brains that we need to involve here to actually make this work together. So that from a prescriptive approach where we have fixed intervals of saying we just, for example, have critical items that we inspect yearly, and then a bit of non-critical items that we then just inspect, for example, every 5 years. We go to a risk-based approach. So because this one, it's not based on information and knowledge about the items, but there we would actually just say we have the standard inspection plan and we just go there. So we hit at the target with a lot of arrows and hoping that we will then by that make sure that the critical items are all okay. Whereas if we use the risk-based approach, we actually focus on the representative inspections and have a risk-based inspection plan. And for that, we need advanced analytics to be able to actually know what is the state of our equipment and when should we go, when will it fail. So this is, for example, how a risk assessment process would look like. This is just to give you an example, and the presentation, I'm happy to share the presentation also afterwards, so you can look into that one more in detail. But we have, and this is the big part, what I would like to point out here, we have the observation data that goes into this risk evaluation, and that is one of the main parts. So we need to have an operating base, and we need to have the good measurement input to be able to actually do this evaluation of observation data. But that was it so far, just giving you a sneak view into these two topics. To sum it up, it's digitalization is the buzzword that I was focusing on today to say how are we actually operating in the future. I'm super excited to listen into later the experts speakers, how they explain in their specific field how they do the improvements there. And I would like to thank you for giving me the chance to speak here. And I'm happy to discuss with you and take any questions.
Well, thank you, Paula, for this very inspiring talk and sharing with us your experience in the actual application of digitalization in wind farm operation, because there's a lot of talk about this, there's a lot of research about this, but it's important to bring it also to the field and to make experience. So thanks for that. And well, apparently everybody's still digesting your talk, and I can't see any questions at the moment, so I take the chance to ask one question myself first. You showed the enormous value of data for maintenance and inspections and monitoring. One step further could be to also use the data for control of turbines or control of the wind farm. So, for example, by changing controller settings depending on the wind or on the load data you have actual at the turbine at the time. Do you think about that, or do you think this is an option for the future?
I think I have to make sure I understand your question correctly.
Yeah.
So your suggestion would be to directly link the outcomes of this data analysis to the control of the turbine, or?
Yes, if you have operational data from the wind farm and the turbine, and you can analyze the data actually in real time, and can then tell the turbine, well, in your situation, you are in the first row, you have very little turbulence, so you can set your controller in a way that you operate more in getting more energy out, but you don't have to take care of reducing your loads. Or you are the last turbine and you have a lot of turbulence, and it takes up a lot of it produces a lot of load. It takes up a lot of your lifetime at the moment. If you run full power, reduce a bit and optimize the kind of lifetime against power production and things like that.
Sure. Yes, obviously that's one of the main focuses also of the Ørsted lab, to understand better how the turbines perform, and not only in the as an overall wind farm, but per position actually. So one of the projects was actually to optimize the individual turbine performance within a wind farm based on the turbines. So to have a perfect direction, individual direction of the turbines towards the wind. So that is already happening. It's not only about analyzing the data and going into inspection plans, but also the improving the operation, and that was a big project, or is a big project also, that we're looking into, in having the data and using that to improve individual turbine performance, because as you mentioned, the wind direction turbulence is actually different on each of the positions, and if we can find these little tweaks to improve individual turbine performance by, for example, having them directed more towards the wind, or also learning more about the individual loads on the blades on each of the positions. So yeah, that's definitely also something that we're looking into.
Yeah, thank you. Well, questions are coming in. The first one was by Farid. What is the main contributor of floating offshore wind O&M costs based on your Ørsted experience? I don't know how much experience you have, but maybe you have an opinion.
Yeah, thanks, Farid. Very good question, or interesting question. At the current state, we don't have offshore wind farms. So it would probably be easier for a different company who actually actively looks into and develops offshore floating wind. At the current state, I'm not aware of any projects in floating for Ørsted. So I would just have to tell you sorry here that I cannot answer this question at the current state. But I myself am also actively following our own news feed and looking into how the world of offshore wind and also how Ørsted develops in that.
Yeah, thank you. There's another question by Richard Parker. How do you think autonomous systems can contribute to the inspection and repair process? So it's about autonomous systems, a topic we have in the conference later as well.
Yeah. Yeah. Thanks, Richard. It's there. I would I really have loved to have my colleague Simon in here. I think it is something he's looking into, but I'm afraid I cannot answer this specific question. But if it's one of the topics that we have later, I'm happy to listen in there and maybe contribute to the discussion there.
Yeah, thank you. Yeah, there's actually talk later on autonomous systems by Atlas Electronics. So maybe Richard can hear something there and maybe pose the question there again.
Yes.
Another question, Tatiana Suarez is asking, what are your top 1 to 3 priorities, worries, needs regarding data?
Again, they're very specifically about data. So it's we have a good base of data within Ørsted also. We have, and that's what I think what the base is, why we created or why we had the ability to create this Ørsted lab. I wouldn't be able to mention the top 1 to 3 priorities, Tatiana. So I hope it's you forgive me that I can't tell you this is 1, 2, 3. There were again I would need Simon also to jump in and to sign them off and say yes, I agree there. We're definitely talking about having measurement points. So we need the right measurement system. We need to transfer the data. We need to learn more, and this is where research comes in also about what kind of data do we need. So what is the data also that helps us, that gives us the critical information that we need. But again, I'm happy to also take the spec and discuss with my colleague there. And please feel free also to reach out to the colleagues from ORE Catapult and Fraunhofer IWES. And please support me in establishing a contact there. And I'm happy to follow up on the question there.
Yeah, thanks a lot. We'll certainly do that. And it's good to hear that well, you also see the need for research, and probably this is one aspect is quite important, and that I think is that today there's no lack of data, especially not for you at Ørsted, but it is very critical to find out which of all these data is important and can be used for the operation. So that's very important aspect you mentioned there. There's another question by Paul McKeever. Data-driven operation helps to avoid turbine failures and reduce unplanned maintenance. In terms of revenue, which one of the two is most important to you? Is it reducing the loss of production, so meaning improved performance, or is it reducing the unplanned maintenance? What do you feel is the more important in terms of revenue?
Yeah. Also, again, an interesting question, Paul. I'm not sure it is an either or, because obviously unplanned maintenance will always result in a loss of production. So if we have corrective maintenance, that means that the asset already failed somewhere, and depending on how critical the item is, that might results into lost production. So obviously the highest priority is always to have the HSE concern or the HSE concerns, to have our people working there safely, and it's always easier to have planned and scheduled maintenance than corrective or unplanned maintenance. But both of them, and I wouldn't say it as an either or. It's not about it's more important to us to reduce a loss of production, and then we put less focus on the unplanned maintenance. I think it goes hand in hand. So it's important that we reduce unplanned maintenance, that we can predict failures, that we maintain our assets as good as possible to not have much troubleshooting. And the result of that would then be reducing the loss of productions. I hope that answers your question.
Thanks. Yeah, I think it will. There's another question by Farid. You mentioned that Ørsted lab-owned M studies are used to give sufficient feedback to the suppliers of the equipment. Are you also using the data-driven analysis related to the prognosis of failures as an input for your condition-based strategy, if you have any?
Ooh.
Yeah.
Farid, this is a tricky question.
That was partly in your presentation, but it goes a bit further than that, I think.
No, and it's yeah, I fully agree, and it's a really good question, and I'm happy to take that forward to our Ørsted lab. And ask them if that's the if we do that. I know that we're highly interested in further having the Ørsted lab and further developing the Ørsted lab and using the Ørsted lab, and a close collaboration with our suppliers, and also suppliers bringing forward ideas is always warmly welcome. So it's a joint development. It's not us working on it. So it sounds to me like a very nice proposal. And Farid, I'm happy again also to you if you reach out to me, and I'm happy to follow up on that question and make the connection there.
Yeah, thanks. This fits to the next question by Andrew. He writes, Paula, great presentation. There's high competition between developers and between OEMs. Can you suggest where we can all more readily collaborate to take these topics and solutions further?
Mm-hmm. Yeah,
this is a tricky question, I know.
No, it's nice. It's no, I fully agree. It's a good point. I think the competition is also what improves our performance. So it is healthy to have the competition there, but it's also important to collaborate. And I think ORE, Catapult, and Fraunhofer IWES are doing a great job there already in having research projects, and that is exactly what we need. So yes, there is a high need also to get involved, all of the together, the developers and OEMs, to develop joint solutions for operations. And I'm not only talking about the existing markets in Europe, but especially if we look into going into the new markets, there are a lot of projects and individualities, other challenges that we might look into. And it's always important that we have a good collaboration between the OEMs, the developers, and researchers to find out the pain points and jointly develop solutions there. And I think, yeah, a great compliment also to Fraunhofer IWES and ORE Catapult. We have seen great projects, and I hope I can continue to see those great projects there with a good outcome.
Yeah, thank you. We hope too, and we work on that. Another question by Imogen Brown. How will your own M approach change for subsidy-free assets with wholesale power market exposure? So meaning that ensuring turbines are online and operating when power prices are high. Is this something you already are doing or looking into?
1 second, I have to just reread the question to make sure I can. Yeah, no, it's a really good point brought up there. I just to make sure I correctly understand, I think what you're pointing at is that we have an especially high focus on availability when we have high market prices. So yes, I think the focus again, it's in general, we want to have always bring up our availability, and it's the having the additional complexity of a market price also into the equation, that adds some complexity, yes, but it's not been like before. We didn't have challenges of having times when we had a special focus on availability. So it has always been that throughout the year we have certain weather windows and high wind periods when we wanted to make sure that we have a good availability to actually be able to feed in the electricity and provide the green energy. And then we would try to optimize our maintenance windows, our scheduled maintenance for the windows where we have expect lower wind speeds. And the market price would probably just add more complexity to this setup.
Yeah, thanks. I think that's just a remark by Paul McKeever that he also stresses that the HSE aspects are very important, and is glad that you mentioned those. And I fully agree to that, I must say. And then there's one question from Brandon Kelly. Have you managed to connect your SCADA data to your work management system in an intelligent way to connect performance to reliability?
Ooh. So again, here I have to read the question again.
Yes. This is all going very fast here.
Again, I think that question it's I would have to take it back, and I can just highly encourage you, please reach out to the team. I'm really not sure it's a yes or no question, and I'm not sure I can answer that one to the extent, but I'm always happy to take the question back and come back to you on this one.
Yeah, thank you very much for this offer. And well, there are no more questions, so I think this were already quite a lot of questions. So thank you again for the talk and also for answering all those questions, which I realize is quite difficult in this fast way. But this, I think, fosters a discussion, and this is very good to have it in the community. So thank you very much. Well, you don't hear the applause you usually hear in conferences, but there are a lot of people listening, and I think it was very, very good to have you here. So thanks a lot. We'll have a short break now until 10 o'clock British time or 11 o'clock Central European time. And then we will start with the first thematic block of this conference. The topic will be site surveys for foundation design and monitoring. We'll have 3 interesting presentations coming. So you have 12 minutes to get a coffee, and see you back then.
Thank you very much, and thanks a lot for the good questions, which really interesting questions. And please reach out to me. I'm happy to follow up.
Great, thank you very much,
great.
Paula.
Thank you.
Thank you.
Have a good
Bye-bye.
day.
Okay, welcome back to the conference VirtualWind II. We have now the second presentation coming up in the blog Site Survey for Foundation Design and Monitoring. And this presentation will be given by Stefan Wenau. Stefan works at Fraunhofer IWES as a senior scientist in the Department of Subsurface Investigations. Just before joining Fraunhofer IWES, he worked at the University of Bremen. He's a geophysicist, and his main expertise are different seismic and acoustic methods for the investigation of marine geological processes. And for the last 4 years, he focused on shallow sediment characterization for the planning of offshore infrastructure, mainly offshore wind farms. So, Stefan, we look forward to your presentation, which is entitled Advanced Methods for Geophysical and Geotechnical Soil Investigation for the Offshore Wind Industry. The screen is yours.
Okay, thank you, Bernhard. I'm sharing my screen. All right. Does that work? Can you see my screen now? Okay, I'm assuming my screen is on now. So thanks, Bernhard, for the introduction. So I'm
afraid it's not up. Sorry, Stefan, it's not up yet.
It's not.
I'm not quite sure what the problem is.
I'll try again. Is it up now?
Not. Yes, now I think it's up.
Okay, very good. All right, so I'm here to talk a bit about the geophysical and geotechnical soil investigation as a pre-site survey for constructing offshore wind farms and for designing the foundations. And in general, that's a rather big topic, and I probably could do a much larger talk about that. So there are quite a few different surveys that are usually being done before the planning and the construction of these offshore wind farms actually starts. And one of those is the usually there's a hydrographic survey and a UXO survey being done, something that Tommy already talked a little bit about earlier. And that's usually something that focuses on the seafloor itself. So it's about the mapping of the seafloor to kind of look at the topography and what the seabed is made of, and whether there are any objects there which might be detrimental to the planning of the wind park. And usually the systems which are being used for that are multi-beam sonar systems for the mapping of the seafloor, side-scan sonars, or even synthetic aperture sonars, as we've seen on the SeaCat now, and magnetic systems for the detection of metallic objects, such as UXOs. And the subsurface investigation of the seafloor is then usually done with the geophysical methods, and it's usually clustered together in a geophysical site characterization. And such a survey would use systems such as sub-bottom profiler, single multi-channel seismics, to construct a geological model through the interpretation of these acquired data, and that would usually be one survey that's carried out. And that actually looks into the seafloor, looks at the sediments down to the foundation depth, looks at also at geological hazards such as boulders or faults that might be, or glacial valleys, for example, where putting foundations for wind farms would not be the best idea. Based on that, usually a geotechnical survey is then carried out based on the results of the geophysical campaign. And the geotechnical site characterization then usually uses cone penetration testing to come up with geotechnical parameters of the sediments, and also boreholes to obtain samples for geotechnical testing. And that would then result in a soil model. So basically a model that has geotechnical parameters that can then be used to design the foundations, kind of the dimensions of monopiles, for example, or suction buckets. Then down here you can see I wrote the integrated soil model, and that's more of a step further. That's kind of being done right now in the industry to some degree, where the aim is to better integrate the geophysical site characterization with the geotechnical site characterization to make this whole process more efficient. But I will come to that a little bit later. And in this talk, I will mostly focus on the multi-channel seismics as basically right now the main tool for the geophysical site characterization. That's also what we mostly do at IWES. I will talk a bit about geological hazards, especially boulder detection, and I talk a little bit about what's been going on with the integrated soil model and kind of what the developments are. So to start out with just some basics on the multi-channel seismic principles for those who may not be so familiar with geophysical survey methods. Seismics in general works that we send out a sound pulse, so an acoustic wave that is being reflected on at sedimentary interfaces. So we call these impedance contrasts, where impedance is basically the change in physical parameters at boundary layers, so such as the seafloor, for example. So there's a change in physical parameters, the acoustic wave is reflected, and then the echo is recorded by either one receiver in the case of single channel seismics, or usually in a long cable, including numerous receivers, so that would be the multi-channel aspect of the whole thing. And this method has been around for decades, mostly in relation to the oil and gas industry for mapping reservoirs and kind of looking at the structure of the seafloor. And it's an excellent method of mapping geological structures. And in the last years, or even a bit longer than that, such data has also been used to kind of go a more quantitative way of extracting sediment properties from these geophysical data. So usually you have a survey vessel that tows the equipment, and the result would be a profile through the underground where we can see sedimentary interfaces as reflectors. So these high amplitude layers here would signify basically changes in sediment property, and the interpretation of these seismic data then kind of allows the building of a geological model of a wind farm area, of a site, basically, whether what you construct in the end could be stations or wind farms. The way that this is then done in reality is usually, you need a ship, you need a survey vessel to do this. There's lots of equipment, and there are three major equipment pieces that are needed for that. There is a seismic signal source which is essential, and the properties of this will also characterize the data that's being acquired. You need recording equipment. That's usually a so-called streamer that's being towed like a big cable. You see the orange cable here on deck. That's a long cable that hosts these acoustic receivers, and the properties of which also determine the quality of the acquired data. And of course, the positioning is essential. So positioning the acquisition equipment, the ship, that is on the one hand, that's important because we want to know where the measurement is most exactly. And we need this information for the processing of the data. So we're kind of coming up with the final data result. These surveys are usually carried out at something like 5 knots, so it's not very fast. But a lot faster than, for example, rough ROV operations. So it's and usually what's being done is that 2D profiles are being acquired. So there's a survey grid over an area of interest, and for example, you would have a profile spacing of something like 100 meters or maybe a bit more, depending on the targets and on the requirements of the client. And if we're shooting a 2D seismic survey, which means that we're just using one recording cable, so we have one seismic streamer deployed and usually one source, which gives us basically one profile along the vessel track. On the other hand, this whole setup can be run as a 3D layout. And 3D meaning here that we basically don't have individual profiles, but we're basically acquiring a full volume of seismic data. And then there would be a number of streamer cables being towed. So this is an example with 4. That's a system that we have at IWES. And and they are towed in a spread behind the ship, and that would allow basically the acquisition of a volume of data. On the other hand, it takes a little more time, is more expensive, but a bit more to that later. Now, when designing a geophysical site survey, then something that's really important is to choose the right equipment. And since this whole industry is basically just not so very old, so this discussion on what's the best survey equipment is, I think, still not really, well, basically an ongoing discussion. There are different sources for seismic or acoustic signals that can be used for geophysical surveying. For example, there are sub-bottom profilers. They have a very high signal frequency. And I include them here, although they are usually not used with a multi-channel approach, but just for comparison, they have a high frequency. There are electrical sources like boomers that have a vibrating plate that produce acoustic signals, or sparkers, which is also an electrical source. The frequencies are a bit lower, so somewhere between 1 and 2 kilohertz, or even lower than that with the sparkers. And then there are sources that use compressed air to produce basically a bubble in the water that produces the signal. And those are even lower frequencies, so something between a few hundred hertz, and for really big air guns, which are usually not, from the oil and gas industry, not used for offshore wind, those can even go way below 100 hertz. And this frequency contents of the sources then determines two things. Determines the resolution, so the higher the frequency of the source, the higher the resolution of the data will be. You see that for a sub-bottom profiler, this might be on the centimeter to decimeter scale, while for air guns, this is more on the meter scale. So if this is the only characteristic, then you going for high resolution would be beneficial for geophysical survey, because high resolution means we see a lot more detail. However, as the frequencies go up, the signal penetration into the seafloor decreases. So with a very high frequency system, we will only be able to penetrate about 20 meters into the seafloor, depending on the sediment characteristics. So finding a balance here between the penetration of the signal and the resolution of the data is always a key to kind of make sure that the data that's being acquired actually fits the purpose of the survey. And in the offshore wind, usually what has been used are often boomer sources with a single channel recording, which has shown not to be the best data for the planning of wind parks. And nowadays, what's being used are mostly sparker sources, which ensure that we have sufficient penetration into the seafloor to actually go down to foundation depth. And they are easy to use with a multi-channel seismic approach. On the other hand, of course, if the signal source is important, the recording of the echoes is also very important. And there we have the seismic streamer, which has a lot of receivers in the cable, which is basically the multi-channel approach, which allows us a high data density along the profile that's being acquired. And and it allows a lot of processing options. So something like something like a velocity analysis can be done, the stacking of the data can be carried out. That's all advantages that has over a single channel seismic approach. The length of the cable then usually has to be optimized for the target of the survey that's being carried out. So you need a certain amount of offsets on the length of the cable to be able to image complex geology, such as tunnel valleys in the North Sea, for example. And then the streamer itself can have different characteristics. So there's the number of receivers, the number of hydrophones, which are the acoustic receivers in the cable, is important. The spacing of these acoustic receivers determines the quality of the data. There's a discussion of using, well, groups of receivers together that may increase the signal-to-noise ratio of the data, but also decrease the frequency content compared to single hydrophones. And this whole discussion comes basically from scaling down existing equipment from the oil and gas industry, which is usually made for deeper waters and deeper targets in the seafloor, and to the ultra-high resolution systems which are being used for offshore wind. So, and that's still a development that's ongoing. So basically to push systems which are being used for offshore wind surveying to provide enough resolution to do the planning of the offshore wind farms, and to be the right equipment for that. The data that comes out of these multi-channel seismic surveys are then these profiles. It's a typical profile here from the North Sea. We have well, down here we have reflectors which are relatively parallel. For first well, we have the seafloor here, and then everything below is basically in the sediment, where we can see that there are deep valleys here which are filled with sediment, and then they cut into the underlying basement, which is in the North Sea. That would be pre-glacial deltas, sands, basically, and that and something like that is then used to come up with an interpretation of the data. So we map sedimentary interfaces, we map these tunnel valleys, for example, and identify different units of the infill. And if these surfaces are then interpolated between the profile in the profile grid, we come up with horizon surfaces over full wind farms. And in this example, you can see here in blue, these are the deep valleys, so we can see topography of this valley structure, which is then a basis to design the layout of the wind farm. Now, I just said that some of these surfaces need to be interpolated between profiles, and I also said earlier that there is a 3D option in multi-channel seismic data acquisition, which basically means that we acquire not individual profiles at a spacing, but we acquire a full volume of seismic data, which means there is no interpolation necessary anymore of the interpretation. And it is a lot more successful in imaging complex structures, such as these glacial tunnel valleys that I was mentioning. They often have a complex fill with glacial till layers or maybe peat lenses. This is also technology that comes from oil and gas, of course, and it's not been part of the surveying for offshore wind to any degree. So there have been some surveys where 3D has been acquired, but it's not a standard method yet, although it holds some benefits for planning wind farms. So if something like that is acquired early on in the project phase, for example, that would mean that there is geophysical data, the high quality geophysical data at every point in the field, which would make changes of the wind turbine layout later on in the project phase much easier to do. But again, it's a bit more costly than 2D acquisition, and usually early on in the project phase there is not that much money available for that. So that's a development where we have to see how that continues in the next years, whether that is something that catches on or not. And 3D in the end gives some more options in doing more detailed seismic interpretation. So we could use something like seismic attributes to look at fine details of geological structures. So for example, on this here, this is a tunnel. It's basically a horizontal cut through the sediments, and we see these light areas here, which are glacial tunnel valleys. So we are able to identify lots of detail in the filling of these tunnel valleys. In this example here, there are even some cable tracks imaged with the seismic data, so cables that are on the seafloor or just a few meters below the seabed, which are visible here in the seismic data. Right, so when the geophysical survey is then done and some locations have been identified where geotechnical testing should be carried out to basically come up with geotechnical properties for the foundation designs, then the geotechnical site characterization is carried out, which is usually done, or which is conventionally done in a separate survey, where CPTs are being taken, so cone penetration tests, where a cone is pushed into the sediment at a fixed rate, and the friction of the cone is used to derive geotechnical parameters. Additionally, boreholes are commonly taken, not as many, but some, to obtain samples for geotechnical testing in the lab onshore. So that then produces a wealth of information. And there are two things. So either these measurements are taken at characteristic spots in the field to come up with a soil model of the whole wind farm. Like here, for example, in this example, such a CPT at this position would actually sample this valley fill while also sampling the basement underneath. So this is a good position to take a geotechnical measurement, because it allows us to characterize different geological units at a time. What's also being done is that this geotechnical testing is being carried out at every turbine location to actually feed into the design process of the foundations. And that gives us a very detailed soil profile at that location. However, if the layout changes, if the position of the turbine changes, this testing actually has to be redone, because a lot of the regulations actually demand geotechnical testing at the sites. So that's what's being done right now, and that's the workflow that's being carried out right now. And I think what's the big discussion in the industry, and what's being done at different places, and which also something that we are working on at IWES, is a better integration of geophysical and geotechnical data. Because, as I already said, this geotechnical point information actually limits the flexibility in the whole project workflow. Because if the layout changes, if turbines become bigger and the layout needs to be changed, that sometimes means that geophysical or geotechnical campaigns have to be redone, and that costs a lot of money. That's something, if that can be avoided, I think that will be a big benefit. And an integrated soil model would then, for example, include the interpolation of geotechnical parameters between these sampling locations of individual CPTs based on the geophysical data. So we would use the geophysical data as a basis to kind of fill our subsoil model with geotechnical parameters. And that's something that's called synthetic CPTs. That's something we've been doing here, something people in the UK and Norway have been doing, and have also been working on quite a lot. Such an integrated model should also include seismic attribute studies, so to basically transfer more information from the geophysical data into the soil model. And there's a nice figure here from Mark Vardy just recently where you see a seismic profile here with lots of detail. So you see lots of reflections that can be interpreted. And then you see here in the colors, you see what kind of information is usually transferred into a geological model, so just unit boundaries. And the detail that's within the units usually gets lost on the way. And if we can come up with a reliable method of transferring more of this information from the seismic data into the geological models, that will produce a much larger wealth of information to use by the engineers in the end. Other approaches are machine learning approaches to find geotechnical soil profiles where there are no geotechnical testing data available. And such machine learning algorithms usually are based on high quality seismic data and neighboring geotechnical information. And then that has been shown to be successful in actually coming up with the trend of geotechnical data at an unknown location. So here you have an example where the yellow is actually the geotechnical data that has been acquired at a position, and then the black line is the reconstructed geotechnical parameters from the seismic data and from neighboring CPTs through machine learning. So it actually succeeds in finding the general trend of this CPT, while not being so successful in managing to capture all the little minute detail in the CPT. But that has, of course, also to do with the quality of the seismic data that this is based on. And then, as a last step, of course, we could go to seismic inversion approaches, where we could try to obtain geotechnical parameters directly from seismic data, and just using geotechnical logs for the calibration of these inversion processes. And overall, this has the aim of this all is basically to come up with geotechnical soil characterization at different locations without actually doing the testing offshore. And that would lead to a lot more flexibility, probably a lot of cost saving, if that can be done in a way that it can be used by the engineers to do foundation design. Right. So that was a lot about the soil models, and that usually deals with seismic units and the properties of these seismic units. And something that's usually not included in this are small-scale obstacles, such as geological hazards, such as boulders, for example. And boulders, as you probably all know, they are basically stones which have been transported to the North Sea and the Baltic Sea region by the glaciers during the Pleistocene from Scandinavia, and they are defined as any objects with a size that's from like 0.5 meter to several meters, and they may be really detrimental to pile installation. So either these can be pushed aside by the installed pile, or they might damage the pile, or actually lead to the refusal of pile installation. So that's actually a big hazard that people worry about. You see some examples here from the Rügen chalk cliffs or from the Baltic Sea coast. So things like that are everywhere, and also offshore they are usually in the glacial till sediments can be encountered there. And what's conventionally been done to map these or to kind of assess the risk for boulder occurrence is that we use standard reflection seismic data to look at diffractions. So diffractions, in contrast to reflections, diffractions occur when objects are small compared to the wavelength of the signal that's being sent. And then we get these in seismic sections. There are these diffraction hyperbolas, which are common, and they can be mapped in stacked sections to come up with an estimate of the risk. However, 2D seismic data then has ambiguous localization of these diffractions because it's not clear where the object actually sits. It could be offline or beside the profile, basically. And such things can be dealt with if 3D data is available. So here we see 3D seismic data, or this is GPR data now. It's a horizontal cut through the subsurface, and you see these little circles here, which are also all diffractions. So 3D data can be used to map these diffractions relatively accurately, but then again, 3D data is quite expensive to do. There are also some other technological solutions to that. Well, it's not a new problem, so people have been thinking about that quite a lot. So there are things like a very high resolution 3D chirp application that is good at detecting objects in near seafloor sediments, so down to a depth of a few meters. And so it's not really applicable to monopile foundations where the monopiles are of the length of something like 30 to 60 meters. And there are systems from Pangeo, which they call the acoustic core, which is a seafloor-based system, which then scans a location on the seafloor to foundation depth and can detect objects, but then this cannot be done in a survey method, so the system has actually to be actively set on the seafloor. So we've been working at IWES for some time now. Is a system we call the Manta Ray, which is a dedicated diffraction imaging system for boulder detection, and which comes also from this multi-channel seismic approach, but where we don't focus on the reflection content of the recorded wave field, but we actually look at point diffractions, so things like boulders in the sediment. And for that, we have come up with an acquisition layout that allows us the separation of the diffracted and the reflected wave field, because diffractions are usually a lot weaker than the reflections, so we have to extract them from the recordings. And we've managed to boost the resolution of the system to be able to detect objects of sizes down to 0.5 meter to foundation depth of these monopiles through synthetic aperture processing, for example. And that actually allows a risk assessment for individual turbine locations, or potentially also for full field. What we have is a vessel-based system, so you need a survey vessel for it. It's a tow frame concept, so it's being deployed and towed behind the vessel, and it uses standard seismic sources, so like a sparker, for example. And as I said, it can be done for individual turbine locations or for full fields. And the system is relatively new, so we've done some sea trials 2 years ago, and then a first commercial survey last year. And the results from this would actually be a 3D volume of data that would be diffraction amplitudes. So you see here, this are modeling results from the research project. So you see these red colors here actually denote that this is somewhere where there's a lot of diffraction energy in the subsea floor, and these amplitudes can then be used to come up with risk assessment for boulder occurrence. And the system can be adapted to different object sizes. So sometimes it's more important to look at boulders which are more on the meter scale. Sometimes it's more important to look at stones which are more on the sub-meter scale. And then the size of the system can be adjusted to also the depth of interest for the foundation design. And the results that come out of these surveys are then, well, for one turbine location, we look at an area around that, and we can do statistical analysis of these diffraction amplitudes then to come up with a risk estimate. And together with integrating these diffraction imaging results with the stratigraphic interpretation of the seismic data, we come up with target identification with an error margin, and something like that can then be used to evaluate the risk for a monopile installation, for example, if there's a risk to basically hit a boulder during installation, and for micrositing these turbine locations. So you could actually use that to shift your turbine locations to somewhere in the survey area where no objects have been found. So that's quite from our side. That's quite an interesting way of using these multi-channel seismic approaches for something that's actually quite new in the industry. Right, and with that, I'm at the end, and well, I'd be happy to take any questions. Bernhard, thanks.
Yeah, thank you. So I would, at this point, remind the audience to post questions using your Q&A button. As there are no questions at the moment, I think I'll take the chance to ask one myself. That was very impressive what you showed in data and also in pictures. And that brings me to the question, what is missing to substitute corings and CPTs completely? So why do we still need corings and CPTs at the locations of the wind farms? Why can't we use all your great geophysical exploration methods to just find everything we need?
Yeah, I think people have been asking that question for quite some time, also in the oil and gas industry. But well, essentially, all the geophysical methods we employ, so the sub-bottom profiler and the multi-channel seismic, it's always still indirect methods. So we will never really have our object of interest in hand. So there will always be a need for ground truthing. So we will always have to calibrate our methods against the real thing. So I think also this integrated soil model I talked briefly about, it will always need ground truthing. I think the aim of that is just to reduce the number of ground truthings we need. If we can increase the confidence we have in our geophysical methods, and then, for example, seismic inversion property approaches or machine learning, that will reduce the number of ground truthing points we need. It will not eliminate the need for geotechnical testing. I think that's still a very much the basis for the foundation design. In the end, it will be some kind of geotechnical testing. Whether that has to be at every turbine location, I think that's something we have to figure out in the time to come. Because I think some of these approaches are successful at eliminating the need to do that at every location, but rather to rely on on a lower number of characteristic profiles.
Yeah, thanks, Stefan. So there's some work to be done.
Of course.
Still, that's great. There's one question. At what stage of the wind farm development would the manta ray normally be deployed?
Yeah, the way we're doing it right now is that that people think about that at a relatively late stage in their project. So when the layout of the wind farm has been decided, and usually the locations of the turbines are set with all the different restrictions that are in place, so geotechnical, geological, and the wind fields. So the layout is there, and then it's about a risk assessment of these locations, whether there is a boulder risk, or whether you have to. I talked about this micrositing, which just means you shift positions of the turbines by a few meters to get away from potential obstacles, and that's usually something that's being done relatively late. The nature of the method actually allows to do that relatively early. So you could go and do a boulder assessment of the full wind farm and then feed that into the geological model. But since the method is relatively new, it's not so common in the industry, it means that it's being done relatively late. It has the potential to be done early, but as I said, it's the same as with the 3D surveying, that it's a lot of money to be spent early in the project. And if you can convince people that they spend that money and it has a benefit for the project early on, I think it would be beneficial to do that early on in the project. But the way it's being done now is that people de-risk individual turbine locations.
Yeah, thanks. It's probably also because the method is still relatively new and it takes time until it becomes industry standard and gets into the usual process. So there's the next question by Andy Emery. What depths can you detect boulders to using the manta ray system?
Yeah, well, the way we've employed it now, we've been doing this to the foundation depth of monopile. So that's some tens of meters. So we've been doing this down to 60 meters. It can be, as I said, the system can be scaled. So we can do this a bit further down. So something like 100 meters, I think, is possible. We will have to, well, it's a bit more complex than that, so the definite answer is always difficult. But the resolution of the system then is a question of the penetration into the seafloor, and with deeper penetration depth, you might lose some of the resolution you have. So closer to the seafloor, it's probably easier to detect smaller objects. Further down, it's then more about a bit larger objects. But we're talking about the upper 100 meters of the seafloor of the sediments. Yeah.
Okay, thank you. The next question is, how much learning do you take from oil and gas sector? It seems like a lot of crossover between the two.
Yeah, that's true. This whole seismic method and seismic geophysical surveying, that's something that's been done in the oil sector for 50 years now or so. So especially, I mean, in Germany, as Tommy already mentioned, we don't have much of this oil and gas industry. But if you look to the UK, for example, most of the surveyors who work in the offshore wind industry, they also do jobs for oil and gas. So there's a big overlap there in the offshore industry.
Yeah, and I think the same applies to the seismic methods, which are taken from the oil and gas sector. Yeah. There's a second part of this question is if Fraunhofer engages with external partners or on the delivery of projects, or if we do it ourselves.
Well, I can only talk about us at IWES and here in the subsurface department, and we partner with other players in the offshore industry. So we do surveys together with other companies as well, and we try to focus on some relatively novel applications of, for example, multi-channel seismics, and then that's kind of the survey needs that we focus on. But we do partner with external companies or research institutes, yes.
Yeah, and maybe it's worth mentioning that we just now at this time are out in the North Sea.
Yes, so we're currently doing a survey.
Doing a survey for the BSH on one of the future German wind farms on the geophysical surveying of the soil. One more question by Jan. Is it possible to provide reliability factors for the seismic explored data?
Reliability factors of the seismic data?
Reliability factors for the seismic explored data. So is it possible to have not only the data itself, but also some knowledge about the reliability of this data?
Yeah, of course. I mean, there's a number of factors that affect the reliability of the seismic data. So there's the resolution issue. In the end, is something that's inherent to geophysical imaging. So there will always be a measure of error there, and well, yeah, of course, that can be quantified. So that's something that's there as well. Sure.
Okay, thanks. And we are running out of time, but I have one last question by Andy Emery again. Is there any variation in detectability of boulders in different sediment types, or is the impedance contrast strong in all sediment types?
Yeah, well, that's a very seismic question. Well, if the impedance contrast between the boulder and the surrounding sediment is non-existent, then well, we won't see it in the end. So it will depend on the geological context, of course. So detecting a boulder that's maybe set in very soft sediment, that will be relatively easy. If you have a boulder set in gravel, that might be a bit more challenging. But in the end, if there's an impedance contrast and the scales match, it will be possible to do that. but it always comes down to the geological setting, and it's something that's and since the method is relatively new, that's also something we're kind of looking into right now. Kind of see what kind of fields we can apply this method to.
Okay, thank you, Stefan.
Yeah,
sorry, but we are running out of time. So thank you again for the talk and also for answering all the questions. And also thanks to all of those who contributed to the discussion by posing the questions. We'll now have a short break, only 4 minutes left until 11:30 British time or 12:30 Central European time. And then we'll have the next presentation. So a chance to get a new coffee, and see you back in 4 minutes. Okay, it's time to continue. Welcome back to the conference. We will now have the third and last presentation in this first block about site surveys for foundation design and monitoring. This presentation will be given by Tony Fong. Tony works at ORE Catapult as engineering team leader of the operational performance team He is a chartered mechanical engineer with over 10 years experience in R&D within aerospace and offshore renewable sectors. And his research focus is in the area of design and analysis of structural mechanical systems, with a background of integration design from the civil aviation industry. Tony, please share your screen with us, and we look forward to your presentation, which has the title From Research to Reality, an overview of the marine survey and inspection challenges faced by offshore wind in the North Sea and how technology is evolving from research to reality to address these. The screen is yours.
Thank you. Can you see that screen okay?
Yes, everything's fine.
Perfect.
Great.
Thank you, and thanks for the introduction, and apologies for the long title of my presentation. But it's great to be here today. I'm going to take a bit of a step back compared to the previous presentations we've had, and look at how we actually get technologies from concept through to reality, so from research to reality. This is a key role of ORE Catapult and also Fraunhofer as well in helping this commercialization. So I felt it's quite important to have a focus on this. Okay, so really, as the title suggests, today is all about the North Sea. And I just want to take one moment to reflect of an incident in the past, around 32 years ago now. We've seen the Piper Alpha disaster on one of the oil platforms. And I felt this was just a good moment of reflection to remember that the decisions that we make throughout the supply chain, throughout the development and design of these new industry technologies, all has an influence on safety. So just to remember that the North Sea is such a hostile environment and hard to work in, but just highlights the importance of what we are doing now in terms of technology and improvement of safety and performance of our assets in the North Sea. So with that said, the North Sea isn't a completely new area. It's always been there, and industries such as oil and gas have been using the North Sea for a long time. So what is the challenge for offshore wind moving into this space? So before I talk about specific technologies around survey and monitoring, let's take a quick look at the North Sea itself and the challenges that it poses to the industry. Now, we know from offshore wind that it has seen rapid growth across the EU and also worldwide, with the decrease in the cost of energy coming down rapidly and actually faster than initially anticipated. A number of factors influence this. So we've seen larger turbine capacities. So this graph shows the bars show the average turbine capacity of a single turbine over a number of years, and you can see that this is increasing from where we started of using 2 or 3 megawatt turbines, and now we're talking about 16 megawatts and 10 megawatts plus in the next decade. So that's really driving costs down and the economics down, improvements in economics to help the cost. We're also seeing experience-based optimization as well. So as industries grow, we mature, we understand more, we learn more, and therefore can optimize the technology and the operation of our farms. And on from that, as well as technology developments. So it's not all about the turbine. We have the whole supply chain, whether that's manufacturing or right through to operations and maintenance and even decommissioning. And these technologies are continually developing to help reduce the cost. But with cost reduction, we also see a number of challenges come in as well, which we can touch upon more later on in the presentation. But a couple of notable ones are the lost production. The effects of lost production are increasing with the turbine and farm size. So downtime now of a turbine, of a large turbine, would, for say 1 day, would cost you significantly more than 1 day of downtime for a turbine which was maybe commissioned through the last decade. Our operations expenditure margins are going down as well. There's a very competitive market now to reduce the cost of wind, and therefore the industry now has to do more or with less. So we have to become more efficient in operations and maintenance of these assets. And then the big thing which we'll touch on today, which is the size, the accessibility, and the difficulty of the environment we're moving into as well. The North Sea, if we look at offshore wind in the North Sea at the moment, we've got 16 gigawatts of capacity installed of offshore wind, which is made up of around 3,500 turbines or thereabouts. By 2035, there is a plan to have about 136 gigawatts of capacity using around 7,500 turbines. So we can see that there is a trend to really push the capacity up in the North Sea by over 8 times the amount that we have at the moment within the next 15 years. And coming with this, we do see a number of trends increasing as well. So we are moving further away from the shore. And the reasons for this really are to do with available space and the leasing rounds available to the industry as well. So these are moving assets further from shore. Along with this, we do see increased wind resource as well. The average mean wind speeds are higher when you move further away. And the technology advancements are also helping us move into more of the North Sea. The final point here really is the decarbonisation of other industries is very interesting as well. We're seeing a very big push from oil and gas to become more green, and with this is discussions with offshore wind and offshore renewables really, and how to support them through that journey. Again, this graph just shows some statistics around the average distance of the North Sea wind farms from shore, and we can see that there is a trend gradually growing from the current status where we're kind of averaging around 40 to 50 kilometers from shore, pushing way up into the 90s and above the 90 kilometers offshore. So we are moving quite rapidly away from the safety of our shorelines. This is a quick map to show you what it currently looks like offshore wind in the North Sea. Each circle is a wind farm, and the larger the circle, the bigger the capacity of that farm. We can see that, as we expected, most of them are quite closely populated to the countries which I guess they're feeding power into. The other notable thing here is around the foundation type, which they use as well. So each colour represents a different type of foundation, and predominantly almost all of our offshore assets are fixed foundations at the moment, with only a few floating platforms out there, mainly as development platforms. So it's just an interesting thing to note. A lot of assets are currently there. If we take a quick look at the bathymetry as well in the North Sea, we've still got the offshore wind farms marked on these kind of small dots. And what we can really see is that we've positioned them very cleverly so far. They're all utilising fairly shallow parts of the sea. And that's understandable as we grow confidence and their ability to own and operate these wind farms. We start with the easy locations. What's shown by the black boxes here is actually the new ScotWind leasing rounds. So these are the next proposed areas for offshore wind around Scotland. And what we can really gather from this is that we are moving further from shore, but also the water depths that we're going to be dealing with are also increasing quite dramatically. So we're moving from the comfortable zones of up to 40, 50 meters water depth, and we're going now above that, above the 50, 60 meters water depth. where really there is quite a lot of study into floating wind and alternative foundation types to support this. As I mentioned earlier on, the North Sea is not a new place, and what this really shows here, this image shows, is the existing infrastructure out in the North Sea. So these are all the oil and gas infrastructure currently out there. It's made up of surface and subsurface assets, so it can be anything from oil rigs to FPSOs or well equipment, and the black lines are actually pipelines. So it's just emphasising that there is assets out there, and there's going to be a drive to work, I guess, closer with these other industries and assets to coordinate offshore wind as we move further out. We've seen from our last presentations that actually there's a lot of other stuff going on as well in the sea, and it's not as empty as you first think. These blue dots are actually shipwrecks, and we could continue to plot all sorts of information on here, such as unexploded ordnance, marine protection areas, and other aspects. And quickly it becomes very populated and very dense out there. And really, what this again emphasises to our industry is that the growing importance of survey and knowing the lay of the land, as you put it, or knowing the lay of the seabed for both the planning and commissioning of offshore wind farms, but also during the operations and maintenance phases. We've seen quite a lot in the last presentation, which is very insightful around looking at seismic and sediment type activity around the seabed. And again, this just emphasises the message from the last presentation that there's a lot of things going on out there, and understanding the sediment type drives quite a lot of aspects from design through to installation and operation of your foundations. And again, it shows that the North Sea is quite a varied landscape in terms of sediment type. And this, I promise, is one of my final slides on maps. I feel like a geography teacher at the moment. But this is plotting some of the statistics around annual significant wave height and annual mean wind speed as well when we move off the shore of the UK. And what we can really see is, as you'd expect, mean wave height and wind speeds increase as we move further offshore. This is both a good thing and a challenging thing as well, as we can discover when we look at the challenges associated with this information. So, okay, that's all the maps for today. But what are the effects of moving offshore, and how does this really impact the challenges that we're going to see around survey and monitoring? We've discussed a number of I guess, effects of moving further into the North Sea, and from this list is by no means exhaustive, but it's a quick touch on some of the effects of moving into the North, into further regions of the North Sea. If we look at some of them, so say we move further offshore, our transit and logistics suddenly becomes a lot more challenging. Our commute times can maybe take half a day to get to the location, or even more than a day to get to the location, by which time your operations and maintenance strategies are changing from CTV or small vessels through to SOV and big operational vessels. And with that challenge, we're going to see, I guess, a change in the technologies and how we operate some of that survey equipment. With increasing water depth, we're seeing influences on the foundations and structures. Of course, we're pulling information and experience from the oil and gas industry, but the offshore wind is quite still a different industry on its own. And I guess as we see this introduction of new structures, especially floating, we are going to see an emphasis on being able to prove the reliability of these assets. We also see things like diving limitations as well. The offshore wind industry still uses, in some occasions, divers and humans underwater to carry out some activities. As we move further offshore, this becomes less and less feasible and more hazardous. So there's foreseeably a challenge around that. Around wind speeds and the metallurgical conditions, it's becoming a harsher environment, and being able to operate in this environment is going to be more challenging. Being able to obtain better or adequate data quality while operating in these conditions, and doing this in a cost-effective manner is going to be a big challenge. And really, the last one I'll touch upon here is about other infrastructure as well. So the spatial availability, as we've seen in our maps, is going to become more congested as we move out and as offshore wind becomes a bigger portion of the North Sea. So it becomes ever more important to really understand the areas that you're building in. Also coordination with the other industries which we're going to be kind of neighbouring, and the coordination of marine operations. So say for simultaneous operations ongoing out at sea, it's going to be again another challenge. So what does this mean for survey and monitoring? There are quite a few different impacts we could see happening here. It really draws down to cost and safety, however. Quality is the other aspect, which I've kind of omitted from this slide just to keep it a little simpler. But if we just consider cost and safety, we already know that our transit distances are increasing, so that's going to have an influence on survey and monitoring. The downtime of our turbines are going to be more significant, so there's going to be a drive to make sure that whatever actions we take minimize the downtime of these assets and therefore maximize the energy production. Our depths are increasing. We're seeing needs to avoid more and more infrastructure, the coordination aspect, as we talked about, and the evolving O&M strategy is changing. So there's quite a lot of levers changing at the moment and moving, which is both allowing and enabling new technologies to be introduced. So I'll last few slides in this kind of background, and then we can talk about some of the technologies that we at the Catapult have been working with. The quite big question from me today, really is robotics really the answer moving forward? The Catapult and many other organizations have all done independent forecasts about reduced cost and improved safety, and conclude that robotics, autonomous systems and remote operations is one very promising way of achieving these goals for the industry. But there are some common barriers that, from my experience, that we hit for every technology we look at. There's a technological barrier, so can it perform, can it survive in the environment? The economics behind that, will it save on cost? Will it reduce the time and improve efficiency? And if so, by how much? Regulatory and processes as well. So will this new technique meet the current legislation and standards which we impose at the moment, or that we can foresee coming in the future? And the last one on here, which is often underestimated, the societal impact as well. So the trust and confidence in this technology. Even if you have all of the above and you can prove the technology is fantastic, if you don't have the trust and confidence in the right stakeholders, you quickly lose that edge for your technology. And those stakeholders not only include owner-operators of wind farms, but also right through to people such as investors or even insurance companies as well. So there's quite a large range of stakeholders. And to be able to really commercialize a product, you have to be able to show that it can do all this stuff that we've just talked about to some degree of certainty. And this is where we find a lot of new technology can struggle to overcome these barriers. And this is really the key message I want to kind of focus on today, is about how we do this. What we apply in the Catapult is this verification and validation, or V&V approach, to be able to prove these parts of the challenge and help technologies commercialize. And so this approach is not new, it's not invented by us, but it's an industry developed process around how you carry out development of a new product. Meanwhile, verifying that the product is built correctly and that it meets the user requirements. So fundamentally, it asks two questions. Are we building the correct system? And then also, is the system being built correctly? And as we spoke about, it's an iterative process. It's not a tool on its own, it's just a process which is designed to ensure that we develop some requirements for the system, undertake some design and development work, which is the orange boxes, perform some testing to verify that we have built it to our initial specifications, but then most importantly, this validation loop, which is ensuring that the user or the stakeholders are actually seeing that they have the correct tool for the job. To do this, we have various what we call toolboxes to be able to do these types of processes. I won't dwell on this too much, and what we can do instead is just quickly move on to a number of case studies of technologies from survey and monitoring, which we have been working on recently and are still collaborating on, and show you this verification and validation in action. As we said, marine technologies is a solution to the future of offshore wind in the North Sea. Personally, I think it really is, and hopefully some of these case studies can really emphasize the level of innovation happening at the moment and actually being accelerated into the industry. First project I want to touch on is called MIMRI. This is an Innovate UK project with many partners, which we are involved with running. MIMRI stands for Multi-Platform Inspection, Maintenance and Repair in Extreme Environments. It's a bit of a mouthful, but really it focuses on collaborative autonomy. So we've seen various robotic technologies today being talked about, ranging from ASVs through to ROVs. But the key that we see, especially moving further offshore, is the collaboration between these autonomous systems. So this project is looking at coupling an autonomous surface vessel by Thales, which will undertake the marine operations, carrying equipment out autonomously to a wind farm, and even performing part of the inspection regime by being able to do a wind turbine inspection of the rotor blades without stopping the rotor at all. So again, reducing this downtime of turbine. It's then able to launch an unmanned aerial system to perform closer up inspection, and even to deploy an inspection robot directly onto the blade. The inspection robot, as it is titled, can perform detailed NDT inspection of blades and potentially even basic repairs of blade surfaces. And this is all actually coupled together with some advanced mission planning and optimization technology from Royal Holloway in London. And that technology is actually based on the algorithms and the AI used by NASA on the Mars rover experiments that they have going on. So it's some very cutting edge technology being coupled with the offshore industry. This is a very ambitious product. We're very early in the stages of that development, and really we're the Catapult has played a role in identifying what the industry requirements and needs are, and helping the continual ratification of the development activities that our partners are undertaking. So we have people developing all sorts of robotics here and all sorts of AI. We're really making sure that this validation and verification loop is kind of upheld. So what we see in this project is we're very early stages of this validation and verification. We're only in the first leg of the V, but the Catapult are playing, I guess, an instrumental role at the moment in ensuring that we consult the right stakeholders and that we're building the right tool. Another technology which is currently in development is this iFrog robot. We have experienced, the offshore wind industry has experienced many challenges around structural integrity of monopiles, and specifically around failures of welds or just weld quality, manufacturing quality. Therefore, there's quite a drive to be able to inspect circumferential welds on monopiles, but being able to do so subsea at potentially 30, 40 meters water depth or plus is quite challenging. So we have partners developing a teamed robotic system which is able to clean and perform 3 complementary NDT techniques on welds. It then also has software coupled to be able to undertake automatic defect detection and categorization of those defects as well. But the robot itself is amphibious as well, so the idea is that it can be deployed above the waterline, mitigating the need for any divers, and it itself can traverse down the pile into regions below the waterline and perform accurate mapping of both corrosion but also the weld conditions subsurface by using 3 different sensors that is attached to the robot itself. So as the Catapult, again, our role has been in helping define what the requirements for the system are, and using our industry knowledge and our connections with industry to really emphasize the important aspects for development for the robot. So a lot has gone into looking at not only the technical performance of this system, but also the deployability of it, the ability for someone to get it out onto the asset and deploy it in a safe manner. We're also doing a lot around design of the physical testing for the system. And as we can see in this picture in the bottom, we've actually produced a scale monopile which is installed in a dry dock and going to be used for quite controlled testing of the prototype. Again, this product is still in quite early phase of development, where we've seen the requirements being generated all the way through to component testing happening at the moment, with system testing coming up soon. And again, it just shows the flow and maturity of this technology development. A couple more case studies to go before I finish up. Rovco is another technology developer from the UK who have developed some very unique 3D computer vision and AI augmentation, I guess, for subsea photogrammetry. They can do surveys like the one shown in video there live, and actually produce these really high resolution 3D point clouds on the fly. So it does this live as the robot is flying. The interest from offshore wind around this is that it unlocks a new data set at a quality higher than some other technologies we've seen in looking at the integrity of the foundations. And this becomes important in a number of areas. So looking at things such as the anodes and the corrosion protection systems, through to assessment of the cables, looking at scour potentially as well, and then numerous other aspects which we may see being a challenge for the wind industry. So the system is autonomous, and it's able to ensure that it captures high resolution data and ensures that it can do that while it's out at sea, rather than coming back, building a point cloud and realizing that you've missed part of your asset. Again, Catapult has played a big role in helping define what the requirements are for the industry, but also we've done quite a lot of technical validation, verification for them, checking that verifying that the accuracy of their system meets the next best thing that we have from other surveys as well. We've been working quite close with stakeholders on this, with a few industry partners as well, who are able to do this validation piece for us and witness the testing and understand that the technical verification that we've been doing are showing that the system is performing to a level more so than they require. Okay, so we've spoke about a lot of, I guess, actual survey technologies there. Another interesting area for robotics is around the support systems they have. This project, Project A Vision, with Modus subsea intervention, was looking at the development of the residential capability of this offshore system. So they took a commercial AUV system with the ability of performing visual, bathymetry, side scan and sonar, and sub-bottom profiling. So some quite standard instrumentation, and really extending its capability and reducing its reliance on the need for a support vessel. So really what they did around this was to build a residency system. By all means, it's a docking station with power and comms. So it's able to dock autonomously, subsea potentially as well, so avoiding some of the surface ocean conditions. It can then charge, provide data connectivity to upload its results and download the next mission onto its system. And really, what was interesting around this was around the I guess evolution of their business case from this point, where it was first potentially not economical to deploy a system like this because of the expense of the AUV plus the support vessel. That suddenly changed because you can potentially drop the system off or even have a permanently stationed one offshore and let it do its job without the need for a support vessel. And again, this time we're very far up the validation curve in the technology, and we're really just testing the system at a top level and ensuring that it does the job safely. Again, it's showing the route to commercialization here. And this is the final technology which I'm going to talk about, which is on the far end of commercialization, in that it's already a commercial product. We undertook a demonstration with Bibby Hydromap and IX Blue not long ago, looking at this autonomous survey vessel. We undertook a live demonstration in front of a large number of stakeholders in Blyth, where this system sailed out from shore, went out to a wind farm and inspected a number of offshore turbines. The system itself is quite innovative in that it's been designed purely as an autonomous surface survey vessel. Some clever things behind it allow it to perform survey at quite high speeds while maintaining the data quality. And it's really done by this kind of mast system we've got. There's not too much more really to go into detail there, because if you Google this, you can find out quite a lot of information about the system. But really, this finally just emphasizes again this validation need. And what we achieved here in this demonstration was this final part of the puzzle, which was the user acceptance validation. Being able to show in a real environment that the system was able to perform reliably and obtain the data required. And really, this was the final part of the puzzle in building the trust with the end users of this kind of system. And that really concludes my kind of journey, I hope, that I've taken you on today from research into reality, and how we get there using this V&V approach. We've seen a number of technologies on various scales of this verification and validation area. And it's just important to recognize that there is this, this process in bringing new technologies into market. And organizations such as Catapult and Fraunhofer, I guess, are really well positioned to support on this journey, and is part of our key role in pushing the industry forward into the North Sea. So thank you very much for listening there. I hope that the topic wasn't too broad for everyone, and that it gave a good flavour of the types of things and activities we're starting to see, and the opportunities which are being unlocked as a result of moving into, well, I would call it uncharted territory, but for offshore wind, certainly.
Yeah, thanks a lot, Tony, for giving us this overview of the challenges, but also some solutions for the offshore wind when it moves further out from the shore, and also for sharing your experience at our Catapult in transforming innovation into reality. There is already one question, I think. So maybe we start with that while the others are still thinking. The question is from George. What is the flaw detection sensitivity, so the minimum flaw size that can be detected of the IFROG?
The IFROG project. I don't have that figure to hand at the moment. It's still quite in early stages of development. So the partner on this have been doing lab testing at the moment. I guess all I can say at the moment is that it's competitive with kind of current NDT technologies that you would get from metallics in a laboratory environment. Whether they can maintain that sensitivity when they move offshore is yet to be proven. But we are talking about being able to scan thicknesses and detect the surface through thickness, and also the back surface effects of metals up to 100 millimeters in thickness. The actual flaw size, I'm not sure I have to hand, but I can certainly try and find out. And
yeah, thank you. So I think there are no further questions at the moment. So maybe I take the chance to pose one myself, and more general one. I mean, bringing innovation into the industry always requires this two sides. One side is there has to be technology having the capabilities, and the other side, the industry has to have the needs, which actually needs this technology. When you look at your examples for innovation, what is usually the driver for the projects you showed? Is it the industry need asking you for support for their problems, or is this the innovation people who have new technologies and want to bring them into the industry?
So I think it's both. I'm not backing away from your question, but it is both. And that, again, this is why really the importance of organizations like ourselves, like Fraunhofer and already Catapult, we play an instrumental part. Sometimes the industry don't realize, or just there's so much technology being developed that they get drowned in all the solutions out there, and maybe don't see the high value of certain technologies which are being developed. So sometimes they're not aware of certain technologies, and sometimes the innovation space isn't aware of the challenges. And this is where we do a lot of work collaborating with industry, but also with innovators to understand both sides of the story, and we can play an instrumental part in connecting those two. So one of the ways that the Catapult does it is through this Offshore Wind Innovation Hub, where we have a big collection of stakeholders, owner-operators, who have voiced to us what their challenges are in the industry. So this isn't a specific tool that they're looking for, but more so the headaches which they experience day to day. These are all mapped out online, and anyone in the public domain can see these challenges, and hopefully what we see is a respond to those challenges from innovative solutions, and we help kind of join those two parts of the puzzle. So I believe it's both sides of the story. Sometimes there is tools which the industry are not aware of that we have to help push to the industry, and sometimes it's more of a pool where we have to understand what the industry need is and then pull that innovation from the supply chains.
Yeah, thanks a lot. That's, I think, also our experience. It's always important to have both sides in the view, and that's, as you said, one of the roles we as research organizations have. Well, if there are no further questions, I guess that lunch is waiting and people want to go to their lunch as well. So thank you very much again for the talk and also for answering the questions. If there are more questions coming up, then of course, I think you can be contacted later on as we've heard from the other speakers as well, and of course also via us if needed. This brings the first block of presentations to an end, and we have seen 3 talks and learned a lot, I think. In the first talk, we got a great insight into the actual operation of a particular AUV, which can be used to different tasks in offshore wind farms. In the second talk, we switched topic to seismic exploration, geophysical work, and we learned a lot about the capabilities of advanced seismic surveying for offshore wind farms, for the soil conditions which are needed for building the wind farms. And then in the talk just now, we got an overview about how innovation can take place and how it can be facilitated by organizations like Catapult and Fraunhofer IWES. So I think there are 3 quite different talks to this general topic, and I hope you all enjoyed it and learned something. We will now have a lunch break until 1 o'clock British time or 2 o'clock Central European time, when the conference will go on with the second block of presentations. After the lunch break, Paul McKeever from Catapult will take over as the chair. Paul is the head of strategic research at Catapult, and he will guide you through the second block of presentations, which has the topic O&M concept optimization. So enjoy your lunch and join again in about 45 minutes to the next block of presentations of this virtual wind conference. Thank you.
Vicky, hello.
Hi, Tarek.
Hello. Just want to say that I've joined.
Yep, that is great. We're just on the lunch break just now, so we'll kick off at kind of 1 o'clock. So Paul will come on and introduce you, and then we'll be ready to go. I've got your slides.
Okay, perfect.
Right.
All right. So I can see the screen on Teams. You can't make me a presenter, can you?
No, unfortunately not. Sorry.
Okay, that's fine. So I'll just stay on the audio and ask you to change slides.
Yep,
Okay.
that's absolutely great.
Okay, perfect. I'll just stay on the line. Thanks. Bye-bye.
Perfect. Thank you.
How are you getting on, Vicky? Can you hear me?
Hi, Paul. Yep, can hear you fine.
Great. Okay. I think my video is working okay at the moment. Good.
Yep. Okay, you lined up.
You ready to go?
Yep. I'll send you live now. Okay.
Okay. Okay. Good afternoon, everybody, and welcome to the afternoon session of the VirtualWind II conference, which is being jointly hosted by ORI Catapult and Fraunhofer IWES. So I guess for those who are joining this afternoon, a warm welcome to you all, and for those who are rejoining from this morning, I guess it's welcome back. So this afternoon we have a session which we titled O&M Concept Optimization. So we're going to have 3 interesting presentation themes for the next 2.25 hours, I think is scheduled. So the first theme is leveraging the value of autonomous and remote systems for offshore wind O&M, the EDF experience, and that's going to be presented by Tarek Dawood. And then following that, we've actually got a 45-minute session, which has been split into 2 presentations, and they are going to be presented by Hainju Lee and Chungyang Ye from ORI Catapult. And the title there is the use of AI and machine learning techniques in powertrain condition monitoring solutions. And then finally, we have a session from Jonas Kozenski from Fraunhofer IWES, and he's going to be presenting a topic about simulation of logistic concepts for O&M of offshore wind farms. So just before we go into the first presentation, I just wanted to give you a couple of housekeeping pointers just in case you didn't join us earlier. So essentially what we're planning to do is run the presentations in their entirety. There's a chat box on I think it's on the right hand side of your screen. So if you want to ask a question of the presenter, please put that into the chat box. We'll obviously collate those during the presentation, and then we can answer those after the presentation is finished. For the second session, where we've got both Hainju and Chungyang presenting, we will have 2 presentation slots and 2 Q&A slots. So please, as I say, feel free to use that chat box, and let's get some interesting topic and chat going. So without further ado, I'm going to hand over to Tarek Dawood. So Tarek is lead engineer, R&D expert at EDF Renewables. He's a specialist in O&M asset management for offshore wind. His career has spanned more than 16 years, and he's worked in numerous fields related to maintenance within both renewables and the nuclear power sectors. And he's led the O&M research activities for offshore wind since 2015 in his post at the EDF R&D UK Centre, and that is very much on behalf of the EDF stakeholders in the UK and abroad. So without further ado, Tarek, I'm hoping you're available, and I'll hand over.
Thank you very much, Paul. Just waiting for the slides to come up. Sorry, I can't hear you, Paul.
Yeah, those slides should be there now. Can you see them, Tarek?
I can't see them on the live screen. I can just see your video. Yes, I can see them now.
Excellent. Okay.
Great. Thank you very much. So good afternoon, everyone. My name is Tarek Dawood, and today I'm going to be talking to you about the work that we will be doing at EDF about, looking at the use of autonomous and remote systems for our offshore wind O&M activities. And I'm going to give you an introduction to the overall activities, and then look at some specific case studies that we've been doing at our Teesside offshore wind farm in the northeast of the UK. So without further ado, can you move to the next slide, please? Could you move to the next slide, please? Because I don't have control.
I think there's a bit of a delay, Tarek, but it's certainly moved on my screen, so okay. I guess it'll get there eventually.
Don't see it yet on my side. Okay, yeah, got it. Okay, within the theme of remote and autonomous systems, we have built like a lot of expertise and experience on the use of this type of technology for offshore wind. Mainly the expertise is concentrated within our R&D center in the UK, because we're considered the offshore wind center of excellence for our offshore wind activities. But we also liaise very closely with colleagues in France at our R&D site near Paris, as well as our drones competence center, which is based in Grenoble. Really, the main goals that we have with regards to this type of technology is to look at the market and see what is out there in terms of what could be a benefit, and try to validate these type of commercial solutions that we consider innovative. And really what we want to do in this case is to see how these solutions can offer improvements to, speeding up inspections, reducing cost, and perhaps even improving safety. And we do this on behalf of all our global renewable businesses in France, in the UK, and in the US, and now in China as well. And effectively what we want to do is to then move our O&M activities to utilize this next generation of solutions. So we concentrate on all the different types of remote and autonomous systems, from aerial drones to submersible ROVs to autonomous underwater vehicles, and more recently looking at autonomous surface vehicles as well. But even looking at all these types of technology, the innovations may differ in terms of how they work, but overall for us, in terms of using them for offshore wind, the aims remain the same. So what we really want is to make O&M safer, efficient, cheaper, and also try to feed back that experience from O&M back into the design process for our offshore wind projects that are in development to optimize the design. Next slide, please. Still waiting for it to update. Okay, so the first case study that I wanted to talk to you about really is the seabed survey trial that we did at our offshore wind. We wanted to use an AUV to evaluate its capability. We did this in conjunction with a number of contract partners, mainly Partrack, who did most of the data analysis work from the bathymetric data and did the comparisons, and also UTech, who are our service partner, who actually deployed the AUV on our behalf. Next slide, please. I think what I may do is, because it's causing a bit of a delay, I might run through the slides on my own with my own copy. So Paul, just just tell me if the slides have updated, and then I can just work through it. So I'll just think it's now updated to the next slide. So just to give an introduction to Teesside Offshore Wind Farm, so it's owned by our EDF Renewables business. It has a capacity of 62 megawatts, effectively 27 2.3 machines that have been installed, and it was commissioned in 2013. It's very close to shore, about 1.5 kilometers, and in shallow water, approximately about 15 meters in depth. Next slide, please. So in terms of comparing against the current solution that exists for seabed surveys that we use, it's effectively a vessel-based survey that uses towfish side scan sonar, and effectively the way we do it is, we have a dedicated vessel, we engage them, and they go and do the survey over a period of days. The main issue for us, and that results in a higher cost, is the issue of weather variability, and number of instances where we've had weather days where the vessel is just sitting in port, and still we have to pay for that time. So what we wanted to do was try to look at perhaps a different solution where we can maybe combine a number of different activities together, and this is why we considered utilizing the AUV solution, because it can be deployed from the CTV vessel that we use for technician transfer, and the aim really was, while the CTV was going and picking up and dropping off people from the different wind turbines, we could then deploy this AUV, let it run, and then pick it up at the end of the day. Next slide, please. So the AUV solution that we tried for this trial was the Gavia AUV from Teledyne Marine. It's about 2.5 meters in diameter, 100 kg in weight, and has a operational battery lifetime of about 4 to 5 hours. And during the trial, we anticipated a number of times where we would have to swap the batteries out, and this was planned into the survey procedure. So these are some pictures of the AUV being actually deployed in the water. So we used the davit crane to lower it into the water, and then we used this long post to kind of push it out before we started controlling it remotely. But really the aims of the trial were to verify the performance of the AUV in terms of its bathymetric surveying capability against the IHO standard that we need to adhere to for bathymetric surveys, and also to compare the performance and capability of the AUV with the existing vessel-based solutions, so looking at the pros and the cons. Next slide, please. And if you can play the video. So this video effectively shows the deployment of the AUV from the vessel, and a bit later on there is some footage of it working in the water. Within the context, so the AUV actually has to surface periodically to take positioning measurements, and this is part of the survey procedure. Because it's got an autonomous capability, because the route is actually pre-programmed, it can cover a wide area in a very short time. And considering that Teesside is quite a small site, we could cover the selected areas within a day or two. There were a number of practical challenges with regards to deploying and retrieving the AUV. So there were a few times, because the davit crane didn't have the reach, so we had to manually push it out a bit before we loaded it in the water, and then again when we retrieved it, we had to utilize both hooks to bring it closer to the CTV hull and then attach the rope to the hooks and then connect it up to the davit crane, which then lifted it out of the water. But overall, we considered the trial a success because this particular trial happened where a number of other operational activities were also ongoing. So if you move to the next slide, please. The main operational benefits that we proved during this trial was that we were able to do standard maintenance activities that were planned for the day, where we deployed the AUV at the beginning, and then also there was a jackup vessel on site doing a major component replacement as well, and we did this in that environment. So we effectively demonstrated that we could do this type of survey with an AUV when these parallel activities are happening, using just one single boat. Next slide, please. In terms of the data quality and the capability from the measurements that we actually got in terms of the bathymetric data and the analysis. So we determined with the help of our partners at ParTrack that the AUV data complies with the IHO 1A standard. But there were some challenges with regards to positioning that led to errors in the horizontal measurement. So there was a bigger uncertainty in the horizontal measurement. And in terms of the data quality, it was not as good as the vessel-based surveys, mainly because there were some filtering issues that were identified, and also the suggestion was to use a more advanced side scan sonar. So what this effectively proved was that yes, the AUV is good for certain types of surveys, and you can see on the left, at the bottom left-hand corner, the data from the region just around the monopile, where they're looking at the scour for protection, which are effectively rock bags. And in terms of the areas that we looked at very select areas where we could have a comparison between the vessel-based measurement and the AUV measurement, and also areas which had different features. So there were a few that had like rocks and things, and a few were just flat. Also, we wanted to look at the area around the export cables as well. That's something that was of interest to us. Next slide, please. So in conclusion, what we proved was operationally there were lots of benefits in terms of time saving, as well as cost, because when we looked at the cost for a typical deployment from a vessel-based survey and an AU-based survey, we found out that for a sufficiently larger site, and it didn't fully work for T-site, but for a larger site, there were significant cost benefits to be had. Also, I mean, we learned that there still needs some improvements in terms of the hardware capability to improve the quality of the data, and also try to improve compliance with the IHO standard. But this really depends on what precision we require for the survey, and that depends really on the type of application. So we decided that if you were trying to mimic like for like, AUVs need to be improved slightly compared to the current vessel-based surveys. But if we wanted to look at specific areas, then it could be suitable for our needs. So next slide, please. So moving to the next case study that I want to talk to you about. This is another trial that we did at our Teesside offshore wind farm, and this is really about trying to do inspections inside our inside the monopile foundation safely, especially when there are confined space areas that are hazardous, that perhaps require ventilation and additional risk assessments and safety precautions. So could we replace a person with an aerial drone, for example, to do those similar visual inspection checks? So we did this in conjunction with a number of different colleagues in our DTG Drone Competence Center in France, as well as our EDF Renewables business, and with the support of Texodrone Survey and Inspection, who was the service provider. Next slide, please. So just to give you an idea of where exactly we were inspecting. So what you can see there, that's in the red square, is the region we wanted to inspect visually. The platform above is called the airtight platform, and effectively forms the airtight seal between the lower decks, which contains the moon pool area, and the lower working platform from the upper decks. And then this is considered a confined space. Next slide, please. So if you look at the kind of the transition piece and the monopile, that's the region that we're working at. And if you just move to the next few slides, Paul, you'll see there's a number of things that will come up. So that come up. So there's a number of hazardous gases that accumulate in this lower working compartment, mainly because of the internal cathodic protection system that causes hydrogen gas to be produced, and also because of the microbes in the sediment at the bottom of the pile, we also get sulfate-reducing bacteria, which produces H2S gas. So this is a very hazardous environment, and before people can get in, they need to ventilate the compartment and check to see if the atmosphere is safe to enter. There's also a number of safety procedures. So you need to have a person above the platform as a rescue person, and a person to watch over the people going down into the compartment. So if you move to the next slide, which is slide 17. So we utilized a cage drone called the Helios 2 that our service partner Texodrones utilized, and the concept really was to have somebody standing on top of the airtight deck and then deploying the drone through the hatch to do the inspections. Next slide, please. So what we wanted to do in particular was to look at some key areas. So specifically these support plates, or the gusset plates that support the transition piece and the monopile, and there's some grouting between them. And specifically, we want to look at the condition of these support plates. If you move to the next slide, you will see a video. And what this video shows really is the deployment of the drone. And some images of the actual inspection itself. Hopefully we can see it. So what was really interesting in this case was trying this kind of trial out, because from our perspective, no one that we knew had done something like this, to do an internal inspection using a drone inside an offshore wind foundation. And in terms of the types of images that we got and the quality of the images, you know, we felt that it was sufficient that it replicated a person going down and doing it. What was also really interesting was that we were able to test the transmission link of between the person controlling the drone and the drone itself, trying to move between multiple decks. And you can see in the video that you know, we went through multiple decks, flew the drone through multiple decks from that airtight platform right up until the top where the entrance to the tower is. So this proved that we were able to inspect multiple levels from one position, not only below but on top as well, and that the link was strong, and we were able to control the drone. Next slide, please. So in conclusion, I mean, we showed that using a drone can replace a human being in terms of the inspections that we wanted to do below the airtight platform, and you know, we were able to de-risk those activities. So there were a number of safety benefits, but also efficiency benefits, because we could capture that video instead of having a form that we needed to check off in terms of the inspection checklist, and we could do that offline. And also in terms of time of the inspection, it was much more quicker than you would do for a manual inspection. So also we showed that we could fly the drone through multiple levels, and that's really important if you want to, for example, do tower inspections in the future. And now we want to look at, you know, how we can widen the scope of this type of inspection to look at a number of other areas below the airtight flat deck, and also potentially use some additional sensors. For example, can we do ultrasonic thickness checks or such like. Okay, next slide, please. So the next case study that I wanted to talk about is a trial that we did, and a piece of work that we did looking at how do we look at the impact of biofouling on the behavior of our offshore wind farms. And for us, you know, biofouling was a key challenge. I mean, from a health and safety perspective, especially you know, on the access ladders, things like that. You know, we were having to do a lot of cleaning regularly. So we wanted to understand what's growing there, what's their life cycle, but also try to feed into our evaluation of future designs in terms of foundations, and say, well, how does biofouling get taken into account in the DNV standards, and maybe challenge those standards a bit, you know. So we worked again with our colleagues in renewables and also with our service partner Atlantis Marine, who did the subsea inspections. So next slide, please. So effectively, what we consider in terms of the biofouling problem for offshore wind. So you can see on the right is a decommissioned foundation from the Robin rig site, and you can see the extent of the hard fouling, which can be several centimeters thick. So we do know that, you know, biofouling can impact O&M for offshore wind, but the impact could be severe on the foundation structures themselves in terms of their dynamic behavior in the water. But in terms of short-term impacts, you know, like I've mentioned before, there's this issue of hazards when you're transferring technicians from the CTV to the access ladder. Also, as biofouling aggregates on the external surface of the foundation, it reduces the corrosion protection because these grow and then start to fall out, and they flake the paint off and exposing the bare metal. In some cases, also obstructs maintenance activities, and they need to be cleaned regularly in order for us to do those type of maintenance. And then the long-term issues really is about the behavior and the impact on structural integrity of the foundation, especially with regards to hydrodynamic loading, but also corrosion as well. So what we wanted to focus, next slide please. So what we wanted to focus in this particular study really was looking at the impact of biofouling and how it's being taken into account in the standards, and how that reflects in terms of how we as asset owners or developers try to adhere to the standards, when we're writing our ITTs for the foundations, and looking at, are we being more conservative or not? And really, in the standard, what they mention is effectively the marine growth profile at the different depths are effectively, they want to consider it as being more uniform from the water surface right up until seabed. We wanted to challenge this a bit, and this is why we wanted to do this type of trial and inspection, and do some of the structural analysis. So next slide please. So we wanted to first look at mapping and characterizing the different types of fouling that are growing on an offshore wind foundation, like the one at Teesside. So we used one of these ROVs. So the water depth, it was about 15 meters, and we did a full external visual survey from from close to the water surface right up until the seabed, where the scour protection was, and we captured a number of images as well as video footage to post-process later to try to tease out some of the characteristics of the biofouling, but also to map out what type of biofouling is growing. And you can see on the right hand side, the types of fouling that grows on the offshore wind turbine. So initially on the surface you have things like seaweed, mussels, and the hard type of fouling. On the right you can see the right second image from the top, the external anode rings, and you can see the hard fouling aggregating on that. But as you go down further, you start seeing less of the hard fouling, and you see more of the soft fouling, type like starfish and anemones and things like that, and maybe a bit of coralline algae. But it's not as dense as at the top. Next slide, please. So just to look at the different areas that we focused on. So we focused our assessment on the splash zone, what they call the infralitoral zone, and the subtidal zone, which is effectively just below from just below the infralitoral zone down to the seabed. So in the splash zone, it's like I said, it's mainly dominated by things like marine splash midges is what we identified as one, and there's seaweed, which is the purple lava. And in the infralitoral zone, it's mainly dominated by mussels and barnacles. And in this case, these mussels and barnacles, because they're hard biofouling, they add weight and actively increase surface roughness and thickness. And in the subtidal zone, it's mainly dominated by starfish, sea urchins, and anemones. And these are classified as soft biofouling, which has little weight because they're mostly water, and they marginally change the thickness and the roughness of the external surface. But what really this shows, the survey shows, is there is a non-uniform distribution of biofouling, where you have this thick ring of hard biofouling close to the waterline, and this is what dominates. Next slide, please. So what we wanted to do is then take this data that we've gathered in terms of the imaging of the fouling, and we wanted to effectively tease out what the thickness of the fouling is and what the roughness is. And so we took the images from the video and we put it through a software called PhotoScan. It's a commercial software to get the point cloud images of the surface. And then we have some proprietary software developed by EDF R&D. Cloud Compare is actually open source. You can find it on the internet, which allows you to play around with point cloud images, and we can do things like cylinder fitting to evaluate the thickness, and also do roughness evaluations as well. So we did this for a number of different scans, and compile that data. Next slide, please. And what we got with these, surface profiles, where we were able to do some estimations on thickness and roughness. Next slide, please. So then we plugged in this data to some of our structural integrity models. It's basically to evaluate what the impact of this asymmetric exterior biofouling would do to the behavior, dynamic behavior of the foundation. So in terms of the impact on modal frequency, we found that there's a very small impact on the modal frequencies. So this was really an interesting insight. In terms of the effect on the hydrodynamic loading by the waves and the currents, the sensitivity analysis showed that depending on the hydrodynamic loading applied to the foundation, we had scenarios where we had an increase of 75% of the loads, and effectively the parameters that had the largest influence are the roughness of the fouling and the current speed of the water. Again, this is a really interesting insight, which we then fed back to our colleagues in EDF Renewables, so that they have a better understanding of the impact this type of distribution of biofouling can have. Also, what this also shows is that in terms of the DNV standards, perhaps there's some refinement may be needed to reflect, what is really happening in real life. So perhaps they're a bit more conservative. So to conclude, the next slide, please. DNV standards really, that account for biofouling. From our work, we think they are a bit too conservative. And from what we've seen at the T side with the subsea inspections, it shows more of an asymmetric profile of fouling with this hard ring of fouling close to the water surface. And we basically leveraged our expertise in 3D photogrammetry and post-processing to characterize the thickness and roughness of the biofouling that is aggregating on those foundations, and then through the sensitivity studies that we've performed using our modeling, we showed that that realistic biofouling profiles and specific offshore site conditions need to be considered when looking at the design for offshore wind foundations. So this is a good example where where O&M is then feeding back into the design process and then refining what we do for our next round of offshore wind sites. Next slide, please. So to conclude, we're doing lots of different case studies. I mean, these are some of the case studies that we've been doing, but we feel that autonomous and remote systems have a lot to offer, and there'll be a big part of offshore wind farms in the future if they're used in the correct way. And there's lots of innovations around these type of systems, but really the overall aims remain the same. So it's effectively to make O&M safer, more efficient and cheaper, but also to feed back that experience into the design process to optimize future designs. And also effectively to develop this standard process where we're trying to understand the impact of how we use these type of systems to validate their use and then transfer that knowledge back into the business. That concludes my presentation. Next slide, please. So thank you very much for your attention.
Okay, thank you very much, Tariq. Obviously, in the virtual world, you're not going to get a round of applause from the audience, but I'll certainly give you a thumbs up. And well done, and thank you. So I think we've definitely got at least one question in the Q&A about the first project. But before we go on to that, I was going to ask you about the biofouling case study you just presented. So you mentioned about the standards being conservative in EDF's view, and I was just thinking, is it possible to do studies before the foundations themselves are actually in place, and then determine what kind of foundation design you need to go for? I know you mentioned it was site specific, but is that actually possible, and is that a trustworthy way to do things?
So I think the main point that we had was that the DNV standard advised considering biofouling as a uniform thickness. And what we're saying is, from what we've found at Teesside, that it's not uniform, it's asymmetric. Of course, you can do studies to evaluate the impact, and that's what most foundation designers do, because they take their guidance in the standards. But what we're saying is that perhaps considering this uniform thickness, because if it's a uniform thickness all along, it has more of an impact compared with this asymmetric loading, and this is what we want people to perhaps maybe take a bit more notice of, and to consider. And perhaps this may not be the same observations on other sites, but this is what we have found.
Okay, right. That's helpful. Thank you. And the other question I was going to ask you around the biofouling was, you mentioned in one of the slides that there was a 75% increase in hydrodynamic loading, which on face value, that sounds to me like it's quite significant. I mean, were there any alarm bells raised at that point?
So while that was the case, there were a number of assumptions in our model. So while this was, this indicated a cause for concern, I think there were a number of uncertainties around, for example, our structural integrity model, the way we estimated the thickness and roughness. So it was effectively considered that there is an increase, and I mean, while we showed a significant increase, it really comes from the modeling. So I think what we communicated to our colleagues in the renewables business really was, perhaps you need to consider your evaluation and analysis just to check to see if is this really correct or not. So effectively we were challenging the established way of doing things by highlighting some new information and raising it as a concern, but obviously with all of those caveats that while this is a show of concern, they really need to have a look at it in a bit more detail. I mean, this was done over a short period of time, just to evaluate at a very high level what the sensitivity could be.
Okay, well that certainly explains it. Thank you. Yeah. So jumping to the chat box, as I mentioned, we had a question from the audience regarding the AUV case study you presented first up, and the question was, could you please elaborate on how you dealt with the AUV measurement noises? Which filtering techniques have you been getting the benefit of?
So I can't divulge that in too much detail because it was a commercial report that was done by our partner UTech. But I think if they want to speak to UTech, you know, they can. But what I can say in terms of filtering really was just that UTech applied their proprietary method of filtering the data. I mean, they have their own process and a procedure, and effectively what we needed to do was to marry that up with, you know, how our other partner ParTrack were going to do that analysis, and there had to be a number of meetings to communicate what type of data ParTrack were going to be given to be able to compare it with the vessel-based survey. So there were a number of parameters, including filtering, that needed to be agreed for them to perform that like-for-like comparison. I think that's all I could say on that. Okay,
so hopefully that's provided some useful information to the question holder. I'm just mindful of time, Tarek, but I think we've got one more question in the chat box, so hopefully you can respond to this. So this is from Kurosh, I think, and the question is there any example of a drone-based blade inspection?
Oh yes, there are. We have a number of blade inspections that we've been doing on our side. So our service provider in this case is SkySpecs, and they have a capability to do autonomous aerial drone inspection of wind turbine blades. We've now moved from onshore sites to offshore, and T-side was examined. The blades at T-side were examined, I think, about a year and a half ago. And yes, and this capability exists amongst a number of other service providers. It's almost established practice now, where blade inspections are now done by aerial drones, even offshore.
Yeah, I think that's our experience at Catapult as well. That the drone-based blade inspection is amongst the most prevalent as it currently stands. Yeah. Okay. Well, once again, Tarek, thanks very much for your time and your presentation. And
no problem. Thank you very much.
A virtual applause once again. Okay.
Thank you so much.
Right. Thank you. So we're going to move on to the second presentation slot now. So we've got two presentations from two Catapult colleagues of mine. The subject matter is the use of artificial intelligence and machine learning techniques in powertrain condition monitoring solutions. So I think Hainju is going to be first presenter, and then Chungyang is going to follow. So just briefly before the guys speak, Hainju has expertise in powertrain system components, and that includes anything from bearings right the way through to couplings and brakes. And certainly he's been focusing on condition monitoring in recent times with artificial intelligence, data-driven algorithms, with a view to improving reliability and introducing advanced testing methods. And then in about 20 minutes or so, you're going to hear from Chungyang, who his expertise is in power conversion, so power converters, and the electrical side of the powertrain is very much CJ's interest. And he's developed a condition monitoring method for power semiconductors based on advanced artificial intelligence condition monitoring algorithms. And again, we're looking at improving the reliability of power converters. So at this point, I will hopefully ask Hainju to join. I can see him on video, so hopefully you'll hear him soon.
Thank you very much, Paul. And okay, I start to share my screen first. So I hope everybody can see my screen now. Okay, yeah. Thank you very much for your attending this section. As Paul described, I'm Hyunju Lee, working for Wally Catapult as a leader of drivetrain knowledge area to improve the reliability of anything about drivetrain. Today, I present what we've achieved in the area of pitch system health monitoring with machine learning algorithm. In this presentation, I present our approach to identify the bearing issues, and the result will be explained. Okay, why pitch? Yeah, as you can see, according to this pie chart from Wind Europe ORG, the pitch system failure account for most downtime and has the highest failure rate. Because of the increased blade inertia and increased maintenance cost, pitch failure will be more critical on large offshore wind turbine. But when we started this project, there were no effective detection method for whole pitch system, except the SCADA, which provide only low frequency measurement data on temperature or pitch current, some very limited signal. Based on this understanding, we aim to develop a health monitoring method for pitch system with existing SCADA data, so which will require no extra hardware be installed, and this system will generate automatic warning or alarm in advance. So hoped with this system, we hope to reduce the number of unplanned maintenance for pitch system. To achieve all of our aim, we used both of the simulated data and field measurement. Especially for the field measurement data, we used our own 7 megawatt wind turbine, which is located at Levermore in Scotland. This turbine switch on and off individual pitch controller according to the wind condition and some other operating condition. And this internal turbine controller has been improved several times after it started to operate. As you know, the operating condition for pitch bearing and other pitch component is very hostile. For example, very high bending moment from large blade with low speed oscillating or standstill condition happens very frequently. In the offshore wind, individual pitch controller is becoming more common to reduce the load on the turbine structure, but this also increased the small amplitude oscillation on the pitch system, and this increased small amplitude oscillation can accelerate the raceway fatigue or false bridling on the bearing. So we focused to identify how many these small amplitude oscillation can be observed in real field, and also to compare and to check if the real field operation is similar to the design simulation or not. We use this method. To compare field data with the simulated result, we developed a cycle counting tool with the below reference, including bin counting and the range pair counting method. Okay, after we count the number of oscillation for both of the real field and simulated data, we used the Harris method to calculate the bearing life. Okay, this is the measured wind speed distribution. We divided this measured wind distribution with 10-minute average wind speed. And total 36 data set we used for 12 data beam, wind speed beam, which is representing normal power production and cover around 73% of all operating condition. Probability of each mean wind speed to be used for 1 year cycle counting and bearing life calculation. Okay, so just for making clear, to make it clear, these data set were considered just for the comparison of purpose, not for the suitability assessment toward 25 years design life. So we use bearing reference life with a modification factor of 1, and also we only consider mx and my, which is a major the fatigue contribution load component. And also the very small variation of pitch movement less than 0.05 degree to be considered as a stationary condition or the standstill condition. And for this study, we used a double low 4-point contact ball bearing, approximately 4.4 meter size. Okay, this chart shows a correlation between the measured data and the simulated data for wind speed and wind field. So the two study about the fatigue life of pitch system, wind field was regenerated in simulation based on the wind speed measured at the hub center. As you can see, there are some small variation, but the mainstream and trend well match with the measured data, and this, I think, the good correlation we can see in power production also. Okay, this is the bearing life calculation result for 1 year based on the actual field measurement. As you can see, fatigue damage from 1 year operation on the pitch bearing is something like a 3.3%. And what we found there is quite interesting. Based on the same or similar wind field data, we simulated bearing load with some simulating tool, and the result is quite different. Fatigue damage from 1 year operation with a very similar wind field is now counted to up to 32.6%. So almost 10 times more damage has occurred in the simulation data. So why? So we compare the load by load and find simulated load was approximately 1.5 times higher based on average value. And you can see the blue is the actual SCADA data, blue line, MX, and the orange line is the simulated data. And as you can see, it has very similar level of counting number, the oscillation number, but cycle number, but the actual amplitude is much higher. But only 1.5 times higher can result 10 times fatigue damage. There are another one, the reduced total cycle for SCADA. The most frequent amplitude shift toward far smaller range in SCADA real field data. So in simulation, the pitch seems to move more aggressively and more fast. This is an actual pitch position comparison. The yellow one is the simulated one, and the other blue, red, gray line show the movement in real field. As you can see, the simulated data well match with the measured data in terms of the trend, but in local area you can see huge difference. It moves more quickly and more degree changed. So why? This is based on controller tuning from prototype commissioning. So when developer calculate the load on wind turbine component, they normally use the most updated controller, including the IPC or everything. But after that, after controller installed in real field during the commissioning period, the controller tuned for the optimized operation. In this case, IPC amplitude factor was adjusted to maximize the benefit of IPC. But because of some limitation of the simulation tool, this kind of tuning or actual factor itself cannot be applied to the simulation. So that is the major cause of this big difference. So as a result, as you can see, even though the pitch system itself have a very conservative safety margin, the actual operating in field can be quite different with what we expect during the design stage. Fortunately, in our case, the actual load on the pitch bearing is smaller than what we expected. But during the tuning or any other update on the controller can easily increase the load on the bearing or other component, which result quite severe difference in the fatigue life. So that's why I think this situation can explain quite well why pitch monitoring is so important. But the monitoring itself doesn't give us any meaning, because there are more than 1,000 of non-linear turbine operating mode because of the complexity in the wind and turbine system itself. So using the conventional method is almost impossible for us to analyze the condition of pitch system or predict the condition of pitch system. And also, the most SCADA provide very low frequency data from pitch system, and as a result, the most collected SCADA data is unused. So I think we explained why the condition monitoring or health monitoring on pitch system is so important. So to achieve or to develop those kind of system, we filtered the SCADA data to generate normal and fine operating condition and data for that, and use this fine data set to train the machine learning algorithm. So now this algorithm can predict the value of target signal under normal condition with more than 90% of accuracy. So when the measured value is different from the predicted value, this algorithm starts to generate warning or alarm. If this different condition or different condition is continues or increased for predefined time period, this algorithm will require the maintenance on the pitch system. And as a result, I hope this fully automated alarm system allow the operator to be enabled to the predictive maintenance or condition-based maintenance, which result to reduce the unplanned maintenance. Okay, so this is the explanation, and in brief, in summary, we process to evaluate the influence of wind turbine controller on pitch bearing performance. As a case study, the evaluation result with the simulated data set can be different from that with the measured data set. Especially for the pitch system, with the IPC controller, it can be hugely different because of the tuning on the controller or some limitation of a simulation tool. So after that, after we identify the difference between the design load assumption and the actual field data, we developed a machine learning based the pitch health condition monitoring method, which can detect abnormal or normal condition. And again, this is just for the case study, and I'm not insisting this is for every single wind turbine in the world, but it is good enough to identify this can be happen in some area. So we strongly recommend to monitor the pitch system to evaluate the design life itself. Okay, thank you very much. This is the end of my presentation.
Okay, thank you very much. Yep. Thank you. And as I say, another virtual applause for you. Okay, so I think we've got a few minutes for questions. I noticed we have a question come in just a few minutes ago, Heinju. So just reading that out. So it's how do you measure stress in the pitch bearing required for fatigue damage calculations related to the operational data? They're guessing that you have accelerometers, but do you have any load measurement sensor?
That's a really good question, I think. We cannot measure actual stress on the, let's say, the stress between stress on the raceway. At this moment, it's not possible, as I know. So we are also involved in the R&D project to develop those kind of methods, but I think at this moment it's not available. So as you said, we simulate bearing stress based on the wind load from the blade.
Okay.
Okay.
And there's I think there's a follow-up question come in a couple of minutes ago, and it's stating that the proposed degradation model is based on counting the stress cycles. Have you also any experience of working on data-driven degradation models to share?
We are working on developing the data-driven model, but that is also involved in some other the project with the consortium member, so that it will be shared in future sometimes, but not this moment. Yeah,
of course.
Unfortunately, yeah.
So similar to what Tarek was saying in the last presentation, where I think you're pleading commercial confidentiality.
Indeed, yeah.
Okay.
Yeah.
Heinju, I was going to ask you a quick question, actually, a more broader question. So I guess with this condition monitoring, the holy grail, as I would call it, is to get a prognostic capability that is very, very accurate. So in a sense, you're not just analysing the pitch system. You're saying this pitch system is going to fail, and it's going to fail in 2 days' time, or something along those lines. Do you think that is realistic in both the short and or should I say, do you think that's realistic in the long-term future, or do you think it's always going to be the holy grail? I mean, what's your thoughts on that?
Yeah, so I want to emphasize, as you said, in engineering world, everything is possible. So that is actually our aim to develop, as you said. But I think there are some number of obstacles we have to overcome. One is the stress measurement, as someone asked. Without direct stress measurement, it's almost impossible to calculate the counter, the fatigue damage on real field. So that there should be some kind of the method to know exact or accurate level of stress in every time. That is one thing we need to overcome. And also the prediction is we need to tell something happen within some kind of the maintenance period, so that we need to have operator to plan those kind of maintenance during the planned maintenance period. So that without those kind of a buffer, let's say something like 1 day after the bearing will be failed, yeah, that can be considered as a predictive or prediction, but it doesn't have too much for operator. So it need to have a kind of the long-term prediction. So this is also one other thing we need to overcome, because of the current fatigue damage calculation is based on the SN curve, and those kind of SN curve of material has a huge variation of let's say the deviation. Yeah, so we hope to develop, and that will be achieved in somewhere future, but not in short term, I think.
Yeah. Okay. I'll continue to watch with interest.
Thank you. Yeah.
Right.
Yeah.
Thanks once again, Hanju. Thank you very much. So just before I move on to the next presentation, I noticed there was a question from Fergus Rowe that was for Tarek. I'm not sure Tarek is still with us connected, but I'm sure that somebody from Catapult or Fraunhofer can forward that question on to Tarek and hopefully get you an answer remotely for that one. Fergus. Okay, so as you've seen from Hanji, you've had a presentation on where we've used AI on I guess a drivetrain component. We're now going to move on to an electrical component in the powertrain, and CJ is going to present to you the condition monitoring, AI-based condition monitoring, very much from a power converter solution. So, CJ, over to you.
Hello, everyone. I'm CJ. Can you hear me on my screen? All right, I think.
Yeah, it's good. It's good, CJ.
Okay.
Good
Thank you. Yeah. So here is our agenda for today. I will first start with some of the background, and also focus on the heat flux detection method and the upper grid method with artificial neural network, and also share with you guys the test design and experimental results.
CJ, can you share your screen, please? It's not coming through.
Is it?
Can you share your screen, please? It's not coming through.
Okay, I think. Oh, right. Can you see the screen now?
Yeah, but we can see the screen with a smaller current page and the next slide.
Right.
I guess that happens to mine also.
Okay. Is
No.
he? No.
CG, can you change your presenter view, please?
Uh-huh. How to put it? Is this getting better?
We can still see the upcoming slide.
Uh-huh. No.
No.
Right. Okay.
It's fine, just carry on like that.
Okay. Right. So first start is the power converter. So the statistically shows that converter causes about 13% of the failure rate and 18% of the downtime. So converter reliability will be very important to the offshore wind turbines. And then this shows you the pie chart of the failure breakdown. Inside the converter, you will find the power module failure, including IGBT, chopper, rectifier, inverter, and diodes, account for about almost half of the converter failure. So the power module reliability will be more serious in 10 megawatt plus offshore turbine converter. Effectively monitoring the degradation could be a promised way to control the maintenance cost for offshore renewable. Those data from this page and the last one is, despite although it's 10 years old, but it still remains relevant and referenced in our sector. So this shows you the module failure mechanism. In the center part is the inside structure of the power module. From the top to the bottom goes with bond wire on the silicon die, and then go with the direct bonded copper lay on top of the base plate. All these four things are joined together through soldering. However, each material has a different thermal expansion coefficient. So at a certain temperature, each part will have a relatively generated the displacement. So with accumulation of lifetime displacement, the soldering will cause fatigue. They will cause the reduction in the effectively contact area. So it will end up for bond wear, it will cause the top layer is a bond wear lift off. So here it shows you the scan copy of the physically how they are detected. And in the left hand side, it shows you the if it happened to the layers, the solder will cause the delamination. And here they will have an empty part inside the solder layer. So this also shows you the scan copy of this. Accordingly, there are two methods to detect the degradation. First is a thermal-sensitive electrical parameter, which is an electrical method. Another is through the heat flux. Definitely is so. Since 2014, we had started our collaboration with Warwick University, sponsor their research in the heat flux detection. So in the following slides, we're going to show you the most recent outcome of our method. So with the help of simulation, so the process of the degradation can show in the left-hand side, which in the middle you can see the squared black square, and also the red curve. So the red one shows you, the black one is the actual physical size of the silicon. The red one is the effective contact area. So before degradation, these two are well lined up together. So it's a star degradation. The things will come from the four corner, so gradually shrinking to a circle. And during the whole process, the solder thermal resistance will increase. However, meanwhile, if you're considering this module is mounted on top of the heatsink, the heatsink calculated thermal resistance is decreasing. So potentially, if you're using combined temperature measurement and electrical measurement, we can detect the degradation level of the power module. However, this degradation is a nonlinear progress. It's also combined well coupled with electro thermal effect. So it's very difficult to decouple this to apply conventional analytical method. So in the meanwhile, during the past 10 years, the data-driven machine learning technology has achieved extraordinary results. The artificial neural network-based solution have shown outstanding performance in classification and regression. So there's a possible way to introduce artificial neural network into the heat flux detection that could possibly detect the level of degradation. So the idea came is that firstly, we can use artificial neural network to estimate power loss. And then the error in between the estimated power loss with the actual measurement can give you the indication of the level of degradation. Then we can use another artificial neural network to make this categorization. So here came with the detailed design. The whole method comes with two-stage neural network. The first stage is the neural network regression model to correlate thermal and electrical measurement. Depending how many level of degradation you defined, so in each level there will be their own level of regression model. So at the first stage regression model, we can get the error or residue of the model prediction and actual measurement. In the second stage, it's a classification model is introduced to differentiate the detail level. So in this case, the number of the degradation level you need to be carefully designed, need to balance with available accuracy of your model, as well as with the practical degradation. So here come with the detailed test rig design. So we use a commercial product from Segelken. It's a power module, and then mounted onto the water-cooled heatsink. So in the relatively position location, we put a thermocouple to measure the temperature. Meanwhile, is to more important is to emulate the degradation level. In this case, we define we use an extra pad to add the degradation level. So with one pad, we will increase about 10% of the thermal resistance. After 5 pads are added, the thermal resistance increased by 50%. So once we set up the test rig, how to perform the test to optimize the rig and also the algorithm is getting to be the key. So at each degradation level, we apply 2 tests. One test is the static test, as shows in the right-hand side, on the top of the right-hand side. So in use this static testing, we train the neural network model. So the second test is a dynamic test. So use this test result to validate the first stage testing. So in this case, the artificial neural network, the prediction result shows you in the left-hand side, which is a confusion matrix. So to help you read this one is this table. The x-axis supposed to be the actual measurement. So the actual case there's from level 0 to level 5. So the y-axis is the test output from the artificial neural network. So if you examine the accuracy, it shows you that the level 4 and the level 2 and the level 1, those three have a very poor test results. For example, level 4, there are 455 cases. The ANN model labeled this is to level 5 of a degradation level. So in the level 1 case, all the test results from the machine learning, it tells you is in the level 0 degradation. So there's something wrong in the test, either in the test or the algorithm itself. So after examination, we upgraded the model. We came about it with advanced machine learning. In this case, originally the artificial neural network is only have one hidden layer. So in this version, we came with 3 hidden layers. We called it deep neural network. So in this case, we apply the same set of the data after the training and using the steady state test, training the model, and with the same of the dynamic test, and the results shows in the left-hand side. You can see originally those wrongly allocated number cases are well lined up in the diagonal, which makes the algorithm, the accuracy increase to about 98 average. So it's show, especially in the degradation 1 level case, it gives you 100%. So it's a very good result. So here comes with the summary. So far, our deep neural network-based heat sink flux detection method is proposed to monitoring the module degradation. The proposed method can successfully detect the level even under very complex dynamic condition. So the network proposed is to verify this method using more complicated model, which is a prime pack or IGBT module. So this work is heavily detained by the COVID-19. We hope the lab is reopened and we can start this test as soon as possible. I think that this is pretty much from me. Over back to you, Paul.
Okay, thank you very much, CJ, and thanks for that very timely presentation. So I don't think I've seen any questions in the Q&A for this particular presentation. I noticed there's another one for behind you from Bose. I don't know whether behind you could answer that remotely. Just a couple of questions I've got, CJ. So you've mentioned you mentioned briefly the use of the artificial neural networks and then leading into deep neural networks. So clearly the deep neural networks approach gives you a more accurate result. But is there any drawbacks to using DNN? Or similarly, a similar question might be, could you see cases where the ANN technique would be sufficient?
I think the downside of the deep neural network is that it could be the data is overfitted for this particular case. we might lose the more generalized way. So which need more data to make the to increase the accuracy of the DNN. I think that's the only drawback from me so far I can see.
Okay, so overfitting, right? And I guess in terms of, I mean, with most sort of modeling techniques, you've always got the trade-off between more accuracy needs more computation and potentially more time. I mean, is there anything like that between ANN and DNN, or is it just down to what you said before?
Yes, definitely. The computation time is more sensitive for the DNN. So, but if considering the industrial application, I think there will be more. There are some special CPU or GPU can be trained to do that work. It will be quite simple, quite straightforward.
Yeah, and I guess it wouldn't be a kind of a time penalty, because this is see, if you imagine this being applied to operational wind turbines, even though you might need a little bit more computational time, it's not going to be prohibitive in any sense.
Yeah, exactly. Yeah.
Okay. Right. Okay, well, it is 2:30 now, so thanks very much, CJ, for your presentation, and of course, Heinju as well. So now we're going to move into the last theme of this afternoon's session, and this is going to be a presentation from Jonas Konsensky from Fraunhofer IWES. So Jonas is going to present the simulation of logistics concepts for O&M of offshore wind farms. So Jonas, he studied renewable energies at the University of Kassel. So after graduation, after graduating with a master thesis on statistical post-processing of wind power forecasts at beginning of 2018, he worked initially for an affiliate of the WPD group in onshore wind, and then he joined Fraunhofer at the end of 2019, and is currently a member of the Wind Farm Planning and Development Department, focusing on software development of coast and offshore times, which I'm assuming are two project names. So without further ado, Jonas, I can see you on video, so over to you.
Yeah, thank you, Paul. Thank you for introducing me. And I must say the previous presentations have been quite impressive. So hopefully that works out for me. So you should see my screen. So again, thank you. Thanks for having me. Today, I'm going to talk about the simulations of logistic concepts of the operation and maintenance phase of offshore wind farms. Therefore, I would like to introduce you our tool Offshore Times, talk about the simulation process and the procedure, and give you a few examples about how the results could look like and have to be interpreted. But first, I would like to discuss and point out why a simulation tool for the O&M phase is absolutely required. So as we can see, the O&M cost of offshore wind farms are one of the largest cost components of the LCOE, with a share of almost 34%, and have a significant impact on the profitability of offshore wind farms, especially the logistic concepts and processes and the turbine downtimes are the main cost drivers there. So the O&M logistic processes can be split mainly into three parts. On the one hand, we have the plant maintenance, which is causing small loss productions, activities like calendar-based, preventive, or condition-based tasks are in it. And on the other hand, we have these unplanned maintenance. They are like corrective maintenance, which are responsible for medium to high loss of productions. And last but not least, the replacement of large components come in, and they're depending on cost planned and unplanned maintenance. In the logistic concepts, we see costs due to the choice of the operating vessels and their number, as well as their restrictions due to environmental conditions such as the wave direction or visibility, and also the distance to the operation and maintenance port is defining the concept. We have a lot of uncertainties which have to considered, as well as such as the currents of failures, the availability of technicians, spare parts, ships, weather and other external conditions and factors, the chosen maintenance strategy, and as well economic parameters such as the price of electricity and subsidies. But the most important for us, though, is the logistic concepts, and we are focusing on optimizing that one. So, like I said before, our approach is called Offshore Times. It's a virtual test center for the O&M concepts, and we are able to test many different scenarios or conditions holistically, which offers us the possibility to adapt the framework conditions. So in an iterative process, the logistics concepts can be optimized with regard to various KPIs and O&M logistic strategies. So it's a time-based modular tool, which is considering weather and sea data state time series. So how the framework can adapt it is getting more clear by seeing how the schematic principle of the O&M phase is constructed by us. So we have different modules. So first we're defining the infrastructure and the weather and environmental conditions. After that, we're putting in 2 different modules for the wind turbines, where the weather conditions are resulting in different production earnings, and as well as the reliability module, where the weather conditions are resulting in loads, which are also infecting or the reliabilities of each component. Then the main focus we are putting on is the logistic concept and the infrastructure with its resources, vessels, personnel, and spare parts, and where we take the approach to optimize the whole concept. It has direct influence then on the scope of the simulated maintenance work, which feasibility is determined by the environmental conditions, and the executed work is obviously directly connected to the reliability module. All the maintenance activities are therefore controlled and managed then by the virtual control center, which uses information of the weather forecasts, the reliability module, and the logistic concept to define and set up a work order. And as a result of this impact, it's defining the downtimes or runtimes of the turbines, and therefore the whole energy production of the park, but you can also double check single turbines. Due to all these inputs and the performing of the wind farm, we also have a financial model at the end of the calculation or the simulation, and we can therefore determine with electricity prices and the energy output of the whole wind farm your finance or your income and profit. Because it's pretty abstract when we're talking about a tool and not seeing it, I want to show you our reference wind farm and this example of a simulation. So therefore, I would like to show you a simulation of the Amronbank West wind farm, which have 80 wind turbines in it, where we used the weather data era 5 from 2008 to up to 2017. Behind it's a reliability model of the Fraunhofer IWES based in Kassel. It's called Windpool, The base port of the O&M process is Heligoland, and we're using a logistic concept of 2 CTVs. Therefore, I want to show you a video, and hopefully it works. Yes. So on the top you can see the map of the wind farm, the visualization of the operating vessels at the top. There have the green dots are running turbines. The red dots are turbines which are down. Right next to it in the graph is the shown the open tickets per system, which maintenance work, which defines the maintenance work which has to be done, and the type. You can also see the type of failures and the affected component by its colors. On the bottom left, you see the energy production over the project duration of the whole wind farm. But you can also, like you see now, switch to single turbines and see the production of single turbines. In the middle, you have the failures so the number of failures over the whole project duration. And on the right side, you see the vessel number 2 and its workload over the whole project duration as well. So turbines are not producing energy due to failures, and like I said, are marked in red. Every time a CTV fulfills maintenance task, you then set back the failure, and turbine is getting green. Now I have to switch a little bit because it's moving faster than I am talking. There you can see the simulation, the results of the one simulation run. And each run has its own result for the wind farm's energy production, and as you can see at the end of the duration, the production is getting lower. However, to gain statistically reliable results, multiple runs are necessary, and that's the reason for that. You can see in the last visualized run, it's showing a very low production due to randomly frequent failures. As you can see, almost all turbines are down. In comparison to the run before, you saw we have very low energy production on the bottom left. In the end, like you saw the graph before, in the end, we're able to compare different logistic concepts with each other. Shown is, like I said, the energy production of the farm over its operating years using a O&M scenario with 2 CTVs with a percentile bandwidth of P5 to P95 in yellow, and the P50 value shown in red. The energy projection varies from year to year due to the different weather conditions as well as the turbine downtimes. The diagram, you can see the number of failures over the project duration. So you have a lower energy production due to more failures at the project end. Then the overlap is the scenario we run with 4 CTVs. At the beginning of the project, no big differences between both logistical concepts, but with the increase in project duration, the quantity of failures, like you can see, increases as well, and here shown in the graph. And the concept with 2 CTVs cannot take all actions and tickets required, and energy production so drops significantly. In comparison to that, the concept with 4 CTVs can fulfill the maintenance needs and keep the energy production on a constant level at the end of the whole project duration. So the conclusion to that is that we have with Offshore Times a modular simulation tool which we can adapt to customers' needs and to various framework inputs and adaptations. So we use it to optimize logistic concepts of the offshore wind farms and also compare different scenarios. And then we have the possibility to assess innovations and their impact on all O&M processes taking place during the project and in that particular wind farm. Yeah, thank you very much. That was it, pretty quick. Yeah, thank you.
Okay, thanks, Jonas. And yes, thanks for your very efficient presentation. So I'm just,
I knew I was a little in a rush though.
It's okay, we've got plenty of time for questions, and then we'll see where we get to. I'm just double checking the Q&A box. There isn't anything in there at the moment. I just want just whilst maybe we're waiting for one or two questions to come in on the financial model. I'm assuming that it considers the loss of production as well as maybe the costs of unplanned maintenance
yes.
as part of the simulation tool. Yeah.
Yes.
Yeah, and I mean this was similar to a question that I put to Ørsted this morning. That you know, if you've got a turbine failure, then to me you're going to get hit in two ways. Really, you're going to get hit by the additional costs of unplanned maintenance, and you're going to get hit by you not making the money from producing or converting the energy.
Right.
And I was interested to know which one of those is the more dominant. I don't know whether you can answer that.
It really depends, I guess. So right now, we are trying to figure out if we are assuming that we have a constant electricity price. Definitely depends on the electricity price you're missing with the downtime, and you're missing all the production, and of course on the environmental conditions as well. So it really depends if it's a minor failure or a major failure, which takes maybe longer, and definitely depends on the time when it happens. So if it takes place in the winter times and you're not able to get out there for almost half a year, it hits you way more than the turbine is down. Then it's a small failure in the summertime, and you just can go there and fix it in one day. Then maybe the cost for ships and personnel is then higher, so the cost for taking action is higher. Than during winter times.
I know it's. I think it, and as Ørsted mentioned this morning, they kind of go hand in hand, and it's not such a straightforward question because, as you say, if the downtime's huge, and that might be due to the effort to replace the component that's failed. You know, so obviously replacing a gearbox in some of the older turbines is much more significant than maybe changing out a power converter module, for example. But also you've got the weather window as well. So if you, depending on the time of year or the particular weather that you're experiencing, then it may take much longer to be able to access the turbine and make the repair. And that always strikes me that may also drive the interim, certainly the interim solution. So there may be, as part of that unplanned maintenance, there may be some sort of interim solution planned or some prevention method, such as derating the turbine. And this is where the condition monitoring is quite useful, because if you know that something is looking a little bit unhealthy, then maybe you can prolong the operation by derating or something similar until the next scheduled maintenance period.
Yeah, definitely preventive is always better than unplanned. So
yeah, sure.
Yeah.
Okay.
But maybe I didn't point it out. So we are considering these weather windows and the accessibility and feasibility of work as well. So if there's a failure occurring in the winter times, we're considering that the ships might not go out, and we are using the restrictions of each activity and then determine if the work is feasible or not.
Yeah, sure. Okay. The other thing I was going to ask you was in your biography, you also make reference to Coast. I'm assuming that's another project. Is that similar to this one, or?
So we have the O&M tool, which is Offshore Times, which is just there for simulation, the O&M phase of the wind farms. And then we have a similar tool for transport installation. So we have a project plan based T&I tool where you can calculate your cost with the weather adjusted time series module for transport installation activities for wind farm. Where we're also considering restrictions of vessels, multi-dimensional restrictions, and kind of sort of that.
Okay, and I mean, are you seeing? I mean, EDF. So Tarek from EDF, he presented a vast array of autonomous solutions. You know, I think we almost went through the full range from AUV, drones, and also ROVs as well. I mean, are you finding those kind of solutions are making a big difference in terms of, you know, maintenance efficiency, maintenance costs?
Interesting you ask, because it's part of one project we are doing right now. So we are doing right now trying to underline the impact, or doing research in the impact of such innovations like RVs or drones or whatever to figure out some failures and doing maintenance works. Yeah.
I guess, and clearly they will be making certainly a big impact in terms of health and safety as well, because as certainly as the collaborators that we work with at Catapult, there's a big drive to certainly minimise the manned operations, O&M operations, and ideally to eliminate the unplanned operations that involve personnel going offshore. Okay, so I think I'm just going back to the Q&A box, and it looks like you've pretty much answered everybody's questions there, to be honest. We don't have any additional ones. So I think what I'll do is I'll maybe spend a couple of minutes just wrapping up the afternoon session, and I'll keep an eye on the Q&A just in case anybody does have any final questions. So I guess starting with yourself, you've presented the Offshore Times modular simulation tool, which was very interesting, and I think what struck me is the fact that it's quite flexible, and you can try certain solutions out before maybe the owner operators put them into practice is certainly, to me, sounds a really powerful tool and a powerful capability. And then prior to Jonas's presentations, we had a couple of presentations from my colleagues at the Catapult. So Heinju was focusing on drivetrain technologies. So he was looking at artificial intelligence and machine learning techniques for pitch systems. So within his presentation, we looked at SCADA data and simulations. We also looked at the use of individual pitch control and maybe some of the effects that might have. And then following Heinju, we had CJ moving on to the electrical side, where he looked at the condition monitoring of power converter switches. So in CJ's presentation, he talked about the difficulties of thermal based monitoring and how we could use artificial neural networks, particularly deep neural networks, for effective prognostics. And then obviously we opened up this afternoon with the presentation from EDF. So in that presentation, Tarek Dawood presented us with 3 use cases with a range of autonomous technologies. So we started off with the AUV case study, then moved on to the drone application inside the foundation, and then we had the wrap up where we were looking at biofouling and the use of ROVs and the effects of that on the hydrodynamic loading and the standards. So quite a range of presentations. Hopefully the audience have found that very interesting this afternoon. Apologies for the minor twitches on the IT, but hopefully you were patient and you stayed with us. We managed to get there in the end. And I think with that, we're probably going to wrap up. I'm just checking with the organizer. Did we want to say anything else for the session as a whole, or can we all leave early and and get an extra coffee.
I think there was another question came in for Jonas. Do you want
yeah, I'll just check that. Thanks for that, Vicky. Yes, there was. So we had a question from Dinesh. So Jonas, I don't know if you're still there. I can see you. Yep.
Yes, yeah, I'm there.
So the question was, what are those inputs which are needed to be fed into the model at regular intervals?
So that depends on how you're doing the simulation. So usually we're running the simulation to compare different scenarios with each other. So we are putting in weather data, like I said, over years to have enough runs to have a reliable result. Then we have to put in the concepts, the infrastructure of the wind farm, reliability modules, which can be defined or changed for different turbines, and of course the available vessels and personnel we have in our own port. But during simulation, there are no data we have to change or put in a regular interval into the module. So we're doing our simulation, we're doing our runs, and then we have results for these simulated times. I hope that answers the questions or the question.
Yeah, I hope so too. Thanks for that, Jonas. And yeah, Kinesh, if that doesn't answer the question, then by all means type in very quickly another question. But on the assumption that does answer the question, I think we're going to wrap up now. So before everybody goes, I'd like to thank all the presenters today. Also thank everybody for the participation in the VirtualWind II workshop and conference today. And also a reminder that this session was recorded, and there'll be a recording available very soon via the website. So please watch out for that, and obviously you can watch back any of the presentations you wish to at your leisure once those are available. So with that, I'll say good afternoon. Thanks to everybody, and hopefully see you again soon. Okay, thank you.
Thank you very much. Bye.